We begin now to cover special relativity. And for some of you guys, you've had an introductory level of special relativity. For others, this may be the first time. If you've had introductory special relativity before, you may be able to go through the first few sections faster. Otherwise, this should be sufficient. But when you encounter these concepts for the first time, they're a little bit mind-bending. So give yourself the freedom to struggle a little bit because it's odd. So let's start with what we mean by relativity. All measurements are made relative to something else. So when you measure the speed of a car going by on the road, that is measured relative to you or another car or a tree. You're always measuring that speed relative to something else. And when you had introductory physics, we talk about how the choice of reference frame is arbitrary. The laws of physics should be the same no matter how you look at it. So where you set your origin should not change the laws of physics. The right choice of our origin and the right choice of coordinates can significantly reduce the amount of work that you have to do, but the laws of physics are the same regardless. So we want the laws of physics to be the same. What does this mean? We normally talk about things in terms of an inertial reference frame. So an inertial reference frame is one that is moving at a constant velocity. That velocity could be zero, but it is not accelerating or decelerating. And we have to fix both the origin of the coordinate system and its velocity relative to some reference. What we're going to cover in this chapter is special relativity. The reference frame is not accelerating. If you want to cover accelerating reference frames, that is general relativity, you would have to have someone other than me teach you about that. That includes a discussion of gravitation and the impacts of gravitation on our reference frame. So to start this, we have to first understand classical relativity. We want the laws of physics to be the same no matter what. So we're going to talk about how we transform between coordinate systems. And what we're going to do first is that we're going to build up the mathematical language to talk about this classically. And then we're going to show the consequence of our assumption that the laws of physics should be the same in all reference frames, what that leads to. So we will start with a reference frame. This is fixed to the Earth. And then we're going to have a different reference frame, which is fixed to a train. And in honor of my second child, who absolutely loves trains, we're going to make this not just any train, but it is going to be a Union Pacific Big Boy, and specifically, it is going to be Big Boy 4014. And I'm sure that I'm going to mess up some technical details. I don't know how many wheels it has. I should know how many wheels it has by now. But this is Big Boy 4014. By most measures, the largest steam locomotive ever built. And we have a reference frame which is fixed to Big Boy 4014. And, this is a very large locomotive. Once you get it going, it's kind of hard to stop. So it is going to travel at a constant velocity v. And I am going to use an uppercase V for things that are constant. That is my uppercase V. And we want to be able to describe things in the frame of reference for the Earth and in the frame of reference for Big Boy 4014. The way that we do this, the way that we transform the coordinates, is a Galilean transformation. So the coordinates on the train in the x direction, we're lining up the velocity entirely in the x direction. So the position in x prime is x minus vt. So wherever you are, we're going to start them at the same spot at the origin, and you have traveled a distance vt at time t. So if you want the x prime distance, it is x minus vt. And then in the Galilean transformation, the other coordinates do not change. And we're going to sneak in time here, because that will come up when we get to relativity. So we assume that time is the same no matter what. So the only coordinate that is changed is the x direction. And then if we want our position vector in the moving coordinate system, this is just the position vector in the stationary coordinate system minus the velocity times time. And we can take the derivative of this. That gives us the velocity in the prime direction, and that is the velocity in the unprime direction minus the velocity of the coordinate system. And Newton's laws are invariant under a Galilean transformation. So here, if you take the second derivative of this, a prime, this here is a constant, so you get that a prime is equal to a. And so then we assume f prime equals to f. That is making an assumption that the mass is the same in both reference frames, which is true classically. Experimentally, we also see that when you are dealing with classical speeds, m prime is equal to m. And then so then you want to look at whether or not this works. So early on, no experiment could really tell whether or not the Earth was at rest. The motion of the Earth is relatively small. So within the experimental uncertainties, the sun-centered view, where the sun was at the center of the solar system, was equally valid to that with the Earth at the center. Now, when we get to Galilean relativity, so classical, and the speed of light, the problem is that Maxwell's equations are not constant under a Galilean transformation. And this caused much consternation around the turn of the century, because you would expect that, so we want the laws of physics to be the same in all coordinate systems. But if you look at Maxwell's equations, Maxwell's equations say that electromagnetic waves propagate at what we now call the speed of light. They propagate at a constant speed, which is 3 times 10 to the 8 meters per second. So if you have something moving at exactly the speed of light, the Galilean transformation, because the velocity equals the, so to do a Galilean transformation, you take the velocity in the unprimed frame and you subtract off the velocity of the prime frame. If you do a Galilean transformation, the speed of light is no longer constant because you're changing this speed. So that implies that the speed of let's take, you can take light on Big Boy 4014, you shine it, and now it's no longer moving at exactly the speed of light. So we can take our example of Big Boy 4014 and let us assume that we have light. Let me pick a different color. We've got light shining here. So there is a velocity of c. And then that implies that the velocity here is v prime equals c minus v. So if you do this, then if you have light traveling light traveling on the train, it is no longer traveling at the speed of light c, and that's if the light is traveling in this direction. But if you reverse the direction, here in this frame the speed is c, and then in this frame the speed is c plus v, for light going left and right. So you would not only not have a constant speed of light in all reference frames, but you would have a different speed depending on which direction the light were going in the moving frame. So Newton's laws would hold in all frames, but Maxwell's laws would only hold in one frame. And this famously led to the hypothesis of an ether, that basically there was, in fact, one preferred frame. And so people went about looking for an ether. Now, how did they go about looking for an ether? Well, so if you have a preferred frame, and that frame is the one frame where the speed of light is constant, then in other frames the speed of light should not be constant. Now, by the turn of the century, we knew that in fact the Earth was rotating and turning. The Earth was round. The Earth was orbiting about the sun because the Earth was round and orbiting about its own axis. If the frame of reference of the solar system were the one correct frame, then when the Earth rotates, the Earth would in fact be rotating relative to this preferred frame, which means that the Earth is moving relative to the preferred frame. Now, the speed of the Earth, you can calculate this simply by knowing that the Earth turns about its axis once in a 24-hour period. And if you are then on the surface of the Earth at the equator, the speed of the Earth is about 3 times 10 to the 4 meters per second. And we have to compare this to the speed of light, 3 times 10 to the 8th meters per second. So it is 1 part in 10,000. As you can imagine, experiments around 1900, it's hard to measure that very accurately. So how would you do it? And people had tried, but their experiments were not accurate enough. So Michelson and two physicists, Michelson and Morley, came up with a very clever way to do this called the Michelson-Morley interferometer. What you do is that you take light and you have a beam splitter. So this is a partially reflective mirror. And actually, I'm going to use some color coding. So we're going to take, here's our beam splitter. We have one beam of light which goes here, bounces off of a mirror. So this is a partially silvered mirror, so it doesn't reflect all the light. It lets about half of it through. So you get half of the beam going in this direction. And then you have another mirror here. So you get half of the beam going like this. Let me put some arrows there. So then you have two beams of light hitting a screen. And when they hit this screen, if the path length of the green light is different from the path length of the orange light, then you can measure interference. Now, you couldn't design the interferometer so that those path lengths were exactly the same wavelength on the order of the wavelength of light, because this is 10 to the negative 7th meters. And at this point, well, even still, we can't really machine things that accurately. Even today, we can sometimes measure things that accurately, but we can't machine them that accurately. So, in most cases. So what you have here is you'd be able to measure that there is or is not a path length difference, or rather more specifically, you could tell if it was an integer number of wavelengths, because if this is, say, 375 wavelengths traveled by the blue light exactly, and this is 329.5, that's a half a wave, then they're exactly out of phase, whereas if this is 329 wavelengths traveled by the orange light, then the two light waves will add constructively. So you can't tell whether they have exactly the same number of wavelengths, but you can tell whether or not they both travel the same number, whether they're within an integer number of wavelengths of each other. So far, so good. So the part that was really clever is that Michelson and Morley, this is of course before we knew how wildly dangerous liquid mercury was, they put the entire experimental apparatus in a pool of liquid mercury so that they could turn it easily. Well, first of all, it also isolated it from vibrations to a pretty well. So then, if you line this up so that this one is along the rotation of the Earth, then the orange light experiences a shift due to the speed of light in this direction. Going this direction, it has a plus v speed. Going that direction, it has a minus v speed. And here, this particular wavelength does not have any change in speed. Changing that speed of the wave changes the number of wavelengths. So far, so good. You still would only be able to tell that whether or not they were within an integer number of wavelengths of each other. But when you put the entire apparatus in a vat of liquid mercury, floating on a pile of liquid mercury, you can turn the experiment and you can see if you change the interference pattern, because if you are able to turn the experiment, you're changing the angle that the light makes with respect to the rotation of the Earth. And if there is, in fact, an ether, if there is a preferred direction, then you will see a changing interference pattern as you rotate the experiment. It doesn't even matter whether you've got the direction of the rotation relative to the Earth's rotation correct. It just matters that you should see a changing interference pattern. So the problem is that they didn't see this. The interference pattern stayed the same. And what that was telling them is that, in fact, the speed of light was the same in both frames. It didn't, in both directions. It didn't matter whether or not you were lined up with the direction of the rotation of the Earth. So there wasn't a preferred frame. There was no experimental evidence for the ether. So if there is no preferred frame, and there is no ether because you cannot measure the effect of the ether, then the speed of light is constant in all frames. How can you have the speed of light be constant in all frames? Because that doesn't work with a Galilean transformation. That breaks classical physics. So you then, the stunning thing that we had to do is reject the Galilean transformation. It wasn't that, although what we did first, as you will often see in many systems, people didn't immediately go, well, I guess we got to throw out classical physics. They said, stuff's moving along with the ether. The ether's moving along with the earth, so you're not able to detect this because the ether is moving along with the earth. There were all sorts of corrections trying to rescue classical physics. Ultimately, none of them actually agreed with experimental evidence. And experimental evidence, data, in science, that is the ultimate arbiter of truth. So instead, what Einstein, or the proper German pronunciation is Einstein, but everybody in English says Einstein. He said, well, we're going to reject the Galilean transformation and the concepts of space and time associated with it, and see if there really is, because Maxwell's equations tell you the truth. Maxwell's equations say that the speed of light is a constant. So let's assume that Maxwell's equations are pointing us in the right direction and see where that leads. And that is how we get special relativity. So we are going to go through the postulates of special relativity. First, we define an inertial frame. And this is a funny definition of an inertial frame, but humor me. It is any frame in which the laws of physics hold in their usual form. And what that means is that you can always take the laws of physics and add some patching up and it will work, but we want them to hold in their familiar form. So Newton's laws have to hold in that form, and we'll call that an inertial frame. Maxwell's laws have to hold in the form that we are comfortable with. And so then we have a frame fixed to Earth. It's approximately inertial. When we covered Chapter 9, we talked about rotating coordinate systems. There is some effect from the rotation of the Earth, but to a good approximation, you are dealing with an inertial frame, and a frame fixed to, for instance, an accelerating rocket is not inertial. So we are explicitly excluding forms like what we covered in Chapter 9, where we have these extra fictitious forces, and you need the extra fictitious forces in order to make the math work. We're not going to allow ourselves to have these things patching up the whole mess. So no fictitious forces. So then we're going to, and different books use different notations. So if you flip back and forth between different books for relativity, you should be aware that the notation changes, and watch. Don't just open a book and assume the equations hold. You want to read enough of the book to make sure you know what how it's defining its variables. So we are going to define an inertial frame S, and that is typically constant across books. And it is, so this is an inertial frame. We will define an inertial frame, and we will define a second inertial frame, S prime. This also is roughly constant across books, that usually you line up the velocity along the x-axis. Now you can come up with forms for a more arbitrary orientation. So we are going to make S prime an inertial frame, so it moves at a constant velocity relative to S. And now all laws of physics will be the same in these two frames. We are making an explicit assumption that there is no such thing as absolute motion. There is no preferred frame. We pick a frame and all laws of physics should be the same in all frames. No experiment can show which frame is actually moving. There's no right answer. You can only talk about what you would measure in one frame relative to the other. There is no preferred frame, and that is our first assumption. And the second assumption, or postulate, is that the speed of light is the same in all directions in inertial frames. So it doesn't matter which direction you point the light, the speed of light is the same in all inertial frames. This is an experimental fact. And we are constrained by experimental facts. And what we'll see are the logical consequences of this. Now, it's important to note that the logical consequences lead to small corrections in our daily lives. So we're going to see that that, for instance, when you have time change, depending on the reference frame, the effects are really small for the speeds that we typically move at. We're going to start by going through the first consequence of this, which is the relativity of time, or the effect of time dilation. So we are going to start by assuming that we do a measurement we have measurement of time in a single frame. We will, doesn't matter which one, we will do a thought experiment and just imagine that we have a bunch of reliable clocks and reliable tape measures. At some point, the clocks all agree with each other. At the beginning, at t equals 0 in our first frame. And we will set the origin of that frame to be O. We have two events. So we will have one which is nearby. So we'll say it happens at the origin, and one which is further away. And light has to travel from the second event to the origin for you to know what happened. And you can imagine having little stationary observers to look at the clocks along the entire path so that you can tell what the time is as it travels, so that you know time everywhere. So we are allowed to have instantaneous measurements. And what we are going to do, the thought experiments are also called Gedanken experiments, because this was, of course, originally written by Einstein. By the way, if you speak any German, those papers are eminently readable. It's very straightforward language. All right, so then we imagine, as an example, that we have two things happening. So we have inside of our train, by the way, the Big Boy 4014 is the only working Big Boy locomotive. It is not the fastest steam locomotive. That was the Mallard. So we have a train moving, and if you are in the train, and we're going to assume that you have a boxcar pulled behind Big Boy 4014, if you are observing inside of that boxcar, what you see happen is that there is a little laser here. It bounces off of the bottom of the car, or it comes from the bottom of the car, bounces off a mirror on the top of the car, and hits a sensor down here. And so this is, when it hits that sensor, that is going to be our event. What you see from the perspective of the train car is the light just bouncing off of the ceiling and back. What you see from the perspective of someone watching is that, watching from the ground, is that the light actually travels a much longer path. So this here, this is our prime frame, and this is our stationary frame. So an observer sets off a flashbulb on a train, and it travels to the roof and then bounces back. We're going to compare the time in the two frames. And this travels a distance of h. The boxcar has a height of h. And then when you are in the time frame, so the light travels a time delta h, and it travels at the speed of light c, or sorry, the time is delta t prime, and it travels at a speed c, and that has to equal twice the height. Now, you can look at this in the unprimed frame, and when you look at this in the unprimed frame, this is a triangle. The height is h. The distance here is the speed of the train times the time that it travels. So we have the speed traveled by the light times the speed of light times the time it takes to do this, is then equal to this length. So we've got twice, it goes up, it goes down, and twice the square root of h squared plus v squared delta t squared. All right, so, and, this is actually delta t over 2, because this is half the time that it takes. So I could do a little bit of rearranging, and I am going to solve this for, let's see, this I can put in h equals delta t prime over times c over 2. So here I have c delta t equals 2 delta t prime squared c squared over 4 plus capital V delta t. Look at what I'm writing, not what I'm saying. I am going to square both sides. I get c squared delta t squared equals delta t prime squared c squared plus v squared delta t squared, or divide through by a c squared, and we get this ratio, which we will call beta equals capital V over C. So this is a beta squared. And I get 1 minus beta squared delta t squared equals delta t prime squared, or we'll put it here, delta t equals delta t prime over 1 minus beta squared square root. So the time, if I assume that the speed of light must be constant in both frames, I'm assuming the height is not changing here, and then this light travels longer, it travels a longer distance. So I see that, in fact, if I were to measure the amount of time that it took for the light to bounce off, go from the floor, bounce off the ceiling, and hit a receiver on the bottom of the train, that it would actually be a different time in the two different frames. This number here, which we are going to give another special name, we will say gamma is 1 over 1 minus beta squared square root. So we get that delta t is equal to gamma delta t prime. And this is our key result. Gamma always has to be greater than 1 because the speed of light is the highest. Nothing can be faster than the speed of light. So here I have 1 minus a number, and I get 1 over 1 minus that number. So this is always going to be greater than 1. So then we have to think about what this means. This means that if I measure the amount of time in this frame, in my moving frame, it is always going to be less than the amount of time that I have in my stationary frame. So what the stationary frame sees will be longer than what the moving frame sees. And that is time dilation. Time itself is different in different frames. So we managed to save transformations and save the fact that the laws of physics are the same everywhere, but we had to sacrifice time. Time is not the same everywhere. And this is why it was so hard for people to get this, because it is so uncomfortable to imagine that time is actually dependent on the frame of reference. Now, when we talk about laws of physics, we know that classical physics works extremely well from very small scales on the order of millimeters or even micrometers, all the way up to large scales on the level of the size of galaxies. And it agrees with almost all measurements. But I just told you that time itself is not constant. So how can we explain that? Most of the time, most things are not moving close to the speed of light. So we can take this and look at what in fact happens when you are moving very slowly. When physicists have no idea what to do, we always take a Taylor series. It usually works. So if we are at low speeds, beta is very small, and gamma is approximately equal to 1 minus 1/2 beta squared. So then we can look at what these corrections do. Sorry, this should be a 1 plus beta squared. because here gamma has to be greater than 1. So we can look at what these corrections have to do when you have things that are moving, close, they are moving classically, they are moving relatively slow compared to the speed of light. So we can do example 15.1. We have a jet plane, and we choose to set the jet plane's speed at 300 meters per second. Why 300 meters per second? Well, because that makes the math a little bit easier. So then we have capital V is 3 times 10 to the 2 meters per second. Beta, which is capital V over C, is 3 times 10 to the 2 over 3 times 10 to the 8th, which is 10 to the negative 6th. And gamma here is 1 plus 1/2 times 10 to the negative 12th. So my change is 1/2 of a trillionth of a second. So if I have this flight, it's going to let's assume that I have this plane flying for an hour. Then the time change is going to be 1 minus 1 minus 1/2, or 1 plus 1/2 beta squared. Or that this time will be, let me try to write this out just a little bit more explicitly. Delta t minus delta t prime is then gamma minus 1 delta t prime, and that is going to give me, this time is longer than, so let's assume on the plane it is 1 hour. So this is 1/2 times 10 to the negative 12th times 1 hour is 3,600 seconds. So this ends up being 1.8 times 10 to the minus 9 seconds. So if you're on this plane for an hour, the difference in time between the stationary frame and the moving frame is 2 nanoseconds. So this is tiny, even if we're talking about moving on a plane. Now, we will choose a much larger v. If we choose v is 0.99 times the speed of light, so very close to the speed of light, and subatomic particles frequently get this fast in our contemporary experiments, or even when coming from outer space in the form of cosmic rays, then gamma is 7, and the time that you observe on the Earth is about 7 times that observed in the moving frame. So, and then we can see you can never actually reach the speed of light because you get singularities. If this speed is the speed of light, then you end up with 1 minus 1, and you have a 1 over 1 the square root of 1 minus 1. It is not possible. So we have our limits. Gamma has to be greater than 1. Beta has to be less than 1. And then you get that the time in the moving frame is always less than the time in the stationary frame. Now, this does not say that there is a special frame. It says that the frame is special for the event that happened in it. So in the case of the light bouncing off of the railroad car, the frame of the railroad car was special. The frame of the railroad car was the frame that really mattered for that system, that event. And it's not that there is a special frame, it is that events always take place in the frame that the event happens is special for that event, and the time that the event of the event in that frame is always less than other times. So every other time is larger. This is called time dilation. And we are going to further define this. That special frame is given by a T0. This is the proper time. So the proper time for the event is the time that it takes for the event to happen, the time that it takes for the event to happen in the frame in which it happens. So we actually have evidence for time dilation, which is pretty amazing considering how complicated it is to measure. So in 1941, the half-life of a muon in an approximately rest frame was measured to be 1.5 microseconds. Now, muons are lightweight particles. They are the electron's heavier older brother, and they often come from outer space in the form of cosmic rays, from hitting things in space, from galactic processes with stars, all sorts of things. So you can imagine having a muon that is moving at 80% the speed of light. This corresponds to a gamma of 1.67. So then if you measure if you had a collection of muons all moving at 80% the speed of light, and you measured their half-life in the rest frame of the Earth, so they're moving at 80% the speed of light relative to the Earth, so you would measure that half-life in the frame of the Earth to be 1.67 times 1.5 microseconds, or about 2.5 microseconds. So when you're on the Earth, what you measure is that it looks like the half-life of the muons is longer. What that means is that you will see more muons reach the surface of the Earth than you would predict from the muon's half-life in its own rest frame. And you can actually measure the difference in the number of muons that hit the Earth relative to what you would expect. So the way that they actually measured this is that they measured the speeds of muons at the top of a mountain, and then their survival rate to the bottom. And you can see that more survive and to reach the bottom of a mountain than you would have predicted based on the half-life in the rest frame alone. Time dilation has also been directly measured by putting atomic clocks on an airplane. So atomic clocks are some of the most accurate clocks that we can come up with. So you start with 4 synchronized atomic clocks, and you put some of them on an airplane. And you leave one on Earth, and then you put a bunch of synchronized atomic clocks on an airplane, and you measure the change in the time when the airplane travels around the Earth, and the predicted time was 275 nanoseconds, and it was measured at 273, which was within the uncertainty of both the prediction and the measurement. Now note that when you actually deal with a plane flying around the Earth, you also have general relativity corrections. You can't just depend on the special relativity corrections. But this difference in time was actually measured, which is pretty awesome. And your GPS in your car needs to have these corrections that you need to take into account, corrections due to both special and general relativity in order for your GPS to be accurate at the scale that it is. We can also measure, you can measure length contraction. You can think of time dilation and length contraction as two different ways of looking at the same phenomenon. So for instance, if we go to the muon experiment, if you are watching from the Earth, you see that you think that the half-life is longer, but if you're watching from the frame of the muon, then you think that the length traveled by that the muons travel is shorter, and you will get the same result either way. So let's start with how we actually measure length. And often when you want to get into very specialized measurements, you have to think in detail about what exactly it is that you're measuring, as opposed to just taking it on faith that you're measuring what you think you are. So imagine that you have a moving train. Now, you want to measure the amount of time. You can imagine measuring the length of the train by how long it takes the train to pass. So here I have my frame S, not S prime. Here is my son, and he is watching Big Boy 4014. There's the tender. Big Boy is an articulated locomotive, which means that it can actually turn around the middle. And I should probably figure out how many wheels it's supposed to have. So my son wants to measure Big Boy 4014 as it travels past. So he knows the speed, and you can measure the length as the speed that the train takes to pass times the time that it takes to pass. And in a moving frame, this could be how long does it take from the time when the front of the locomotive passes my son until the time when the back of the locomotive passes my son. So either way, you're going to have L prime equals V T prime. So the time that it takes for the length of the locomotive in the locomotive's frame is the amount of the speed of, well, in this case, it's also the speed of my son relative to the locomotive, times the time. Okay, except now we already told you that delta t is gamma t. And then I can rearrange because these two terms are equal to L. So this is gamma L. So I get that the length in the moving frame is the gamma of the gamma times the stationary frame measurement. Now, this tells us that the length in S is shorter than the length in S prime. So the moving frame is shorter. And we can further specify, now we are measuring the train, so we are going to call L prime L0 instead, and L0 is gamma L, or L is L0 over gamma. So when you're watching the train go by, the train looks shorter because gamma is always greater than 1. So the train looks shorter when it passes. If you think about what the muons see when the muons fly down the mountain, the proper frame for the height of the mountain is the frame of the Earth. So the muons actually see the mountain as shorter than an observer on the Earth is. So from the muon's perspective, the mountain just isn't as tall. Their half-life is the same as it was if they were sitting at rest, but the mountain's just not as tall. From the perspective of someone watching on the Earth, the muon's half-life is longer if it is moving. So this is called length contraction. The length is shorter in a moving frame. And then you also have time dilation. Time is always longer in the stationary frame, or in the frame the event does not happen in. We can then ask the question, are there changes perpendicular to the direction of motion? So what we talked about so far was changes parallel to the direction of motion, that the lengths appear to be contracted when you're in a moving frame. So you can do a thought experiment. Imagine that you have two people. Ooh. This is a little bit, let me try to think of something that's maybe not quite so graphic. We will have two people, and one of them is in the moving frame, and one of them is in the rest frame. And the person in the moving frame, we will make this Bert, and this is Ernie. And when in the book, it's that the moving frame person holds a knife on his head, and the question is if the person who's stationary, as he passes, and is the person who's stationary going to get whacked. Instead, we are going to imagine that Bert has his favorite rubber ducky on his head. And the question is, does the rubber ducky get knocked off? So, from Ernie's perspective, we will assume that they are the same height. Now, of course, Bert's taller than Ernie. Ernie, the rubber duck is Ernie, so Ernie's trying to take back his rubber duck. Does he get the rubber duck? So, Ernie holds out his hand at his head's height as he swings by Bert. And if Ernie's height and all of the direction of motion is here along the direction, it's in that direction. If Ernie swings by and grabs the duck off of Bert's head, he will do that if he is not contracted, if his height doesn't change in either direction because he is moving. So from Ernie's perspective, Ernie is going by Bert. So if the moving coordinate system is, let's say Bert shrinks, if Bert shrinks because he's moving relative to Ernie, then Bert will get to keep the duck. However, from Bert's perspective, Ernie is the one who is moving. So if the moving coordinate system shrinks, Ernie should shrink too. So if they shrink, they both have to shrink by the same amount because there is no preferred reference frame. So because it has to be symmetric, they would both have to be shortened, which means that there are no changes perpendicular to the direction of motion. We can then try to put together all of the things that we have learned to make a transformation analogous to the Galilean transformation, but that's going to work when we take into account relativity. So we're going to have our stationary coordinate system, and this is x, y, And we have our moving coordinate system with x prime and y prime. We've got some point P in the coordinate system, in the moving coordinate system. And, well, it is a point P prime, so it's in the moving coordinate system. And we want to know what P is. So we have said now that the directions other than x don't change. That means that y prime is y and z prime is z. Now, x minus vt is equal to x prime over gamma. This is our length contraction, so we can arrange this so that we get x prime equals gamma x minus vt. And then we are going to note, first of all, that if gamma is roughly equal to 1, this reduces to the Galilean transformation, which it should, because what we want is for our laws of physics to roughly hold when we are working with non-relativistic speeds, speeds that are not close to the speed of light. Okay, so we are going to look at what happens to the time of two events as well. So imagine that there is an event in S. We want to calculate S prime. And there is no preferred coordinate system, so I can take this equation and just switch the primes and the unprimes. But when I do that, I have to change the, so in the primed coordinate system, this thing is moving with a velocity of negative v, so my sign changes right here. And I get this. And I can rewrite this to be I can plug in here for x prime, I can plug this in. So I get gamma x minus vt plus vt equals x over gamma. So this is a little bit ugly, but I can solve it. So I'm going to take this right here, and I'm going to solve it for t. And see, I think I dropped a t prime. This should have been a prime, and then here, this should be a prime. Yeah, that works. Okay, so then I can solve this for t prime equals, I now have a negative gamma minus 1 over gamma times x. So this is my minus 1 over gamma. And I've written it like that for a reason. This is where this term comes from. And then I have a plus gamma. And here I should have I have capital V still, plus gamma VT. Now I'm going to divide through by capital V. And I get a mess. And I'm going to look at this term here. I'm going to start with, so I have gamma minus 1 over gamma equals gamma times, let's see, equals 1 over gamma times gamma squared minus 1, which is 1 over gamma, and then 1 over 1 minus beta squared minus 1 minus beta squared over 1 minus beta squared. So this is 1. This is a fancy way of writing 1, and this is just 1. This is just gamma squared. So this is 1 over gamma. Then here I am left with a negative beta squared. Wait, no, positive beta squared, because I have minus a minus over 1 minus beta squared. But this term, so I am left with beta squared gamma squared over gamma, or gamma beta squared. So this whole thing is a negative. So I have T prime equals negative gamma beta squared x over v. And I had a negative out in front here, so I have a positive, plus gamma t. And I can put this neatly, and I will call it a Lorentz transformation. It replaces the Galilean transformation. And if I go from the prime to the unprimed coordinate, from the unprimed to the prime coordinates, I write it like this. T prime is gamma t minus Vx over c squared. And I can write the same thing for going in the other direction. So then going in the other direction, we can write this as x prime equals gamma, x equals gamma x prime plus v t. So this is assuming, so this is just switching the prime and unprime. So that does change the direction, the relative direction. Let's see. Yeah. And the book has a typo. So then we can take this and we can actually rederive the length contraction by defining the proper length, or L prime, to be x2 prime minus x1 prime. So we are taking the front of the train and the back of the train and putting and calling their coordinates x1 and x2 and x1 respectively. And then we can see what an observer in the stationary frame would measure them to be. So if you look at And the book did have the typo, but I put it in incorrectly because this, yeah, it's that way. So then I can put in x1 prime is gamma x1 minus vt1. So at the time that the measurement is done, x2 prime is the same thing, but swap out the 1s and 2s. And we are going to measure both of, we're going to say T1 equals T2. We are measuring the ends of the train at the same time in the stationary frame. So then x2 prime minus x1 prime is going to be this minus that. And the time terms cancel out because we are explicitly assuming this. So it is gamma x2 minus x1. So we get that L prime, which is the proper length, is just gamma times L. And this is our old familiar equation for length contraction. We can take what we have derived and apply this to example 15.3. So here you're looking at a snake which is moving relativistically and trying to figure out, so someone in a stationary frame, for some reason, these are always rather gory, takes two cleavers as the snake is traveling past and smacks them both down at the same time. And you're trying to figure out if the snake gets hacked to pieces. So the person with the cleavers has them 100 centimeters apart, and the snake is moving. The snake is 100 centimeters. So the person with the cleavers smacks them down right after right when the head hits the front. So the question is, does the snake's back end get whacked? So we have the velocity is 60% the speed of light. So our gamma, which is 1 over 1 minus beta squared square root, is 1 over 1 minus 3/5 quantity squared square root. This thing, you will see that a beta of 0.6 is rather common for the following reasons. So this we can write as 25 minus 9 over 25. So this then is the square root of 25 over 16, or 5/4. So since this is basically the only beta where the numbers work out neatly, this is one of the most common betas to choose in relativistic problems. And then we choose the proper length. The length of the snake is 100 centimeters, or 1 meter, in its frame. And because the length is proper in the frame of the object you're measuring, so that is the proper length. And then we are going to put in a coordinate system. The problem has it be a student smacking down the cleavers, but I'll take the hit. I will be the professor smacking down the cleavers in frame S. And we will have the left one at x equals 0, and the right one at x equals 100 centimeters. The snake is, we'll draw a little snake here. You can't really, I guess you can draw a stick figure snake. So if I draw a stick figure snake, it's really easy. This is our snake. And the snake is an S prime, and in S prime, XL prime is 0, and XR, so let me call this X tail and X head. It's 100 centimeters. So now what we're going to do is find X tail in the unprimed coordinate. So X first of all, we have X equals gamma X prime plus V T prime. And we're going to measure them at T equals 0 in the snake's frame. So X tail in the unprimed frame is gamma times 0 plus 0 is still 0. X head in the unprimed frame is gamma times 100 centimeters plus, this should have been here. I'm going to back up a little bit because we have to figure out what events we are looking at. So we know the cleavers slam down at T equals 0. So in the unprimed frame, in my frame, I slam down the cleavers at T equals 0. And then the snake so at T equals 0, that's when the two cleavers go down, and the question is, where do I see the snake's head at that time? And here, yes, that's because my notes have, so we have X equals gamma X prime minus I have X prime equals gamma. This is the X prime equals gamma X minus VT in the unprimed frame. So my tail we're at T equals 0, so I have gamma times 0 is 0. Well, this is gamma times 0 X tail. So X tail is simply 0. I use this same equation, X prime head equals gamma, and then X head in the unprimed frame, except here X head is 100 centimeters and gamma is 5/4, so X head in the unprimed frame is X prime head over gamma, which is 4/5 times 100 centimeters, or 80 centimeters. Okay, now from the snake's perspective, so this is what I see. I see from my perspective that both cleavers go down at t equals 0. The snake's tail is at t equals, the snake's tail is right by this cleaver, and the snake's head is 20 centimeters away from this cleaver. Now from the snake's perspective, so these two events in my frame are simultaneous, but they are not in the snake's frame. So we use our transformation for the time. The time of the tail cleaver going down is gamma t of the tail in the unprimed frame, which is just 0, minus v x tail over c squared. So this is still 0 from the snake's perspective. T head, however, from the snake's perspective, is gamma t head, which is just a 0, minus v x head in the unprimed frame. And now this is not 0. This is negative, this guy's 0. This is negative 5/4 times 0.6 times 1 meter divided by 3 times 10 to the 8th meters per second. So here, if I plug this all in, I get negative 2.5 nanoseconds. So in the snake's frame, the cleaver on this cleaver went down first, followed by that cleaver. So it also sees that the head cleaver misses the head by a lot, but for a different reason. The snake thinks that this cleaver went down and then that cleaver went down. So the snake doesn't get cut. And then we can ask, so the two events are simultaneous in, two events which are simultaneous in one frame are not necessarily simultaneous in the other. And then what you would see actually for where this cleaver goes down, so we have x prime head equals gamma x head minus v t, so head. So this guy in the stationary frame, this is 0, but what you see in the snake's frame is that the cleaver actually goes at 125 centimeters and not, so it's at a different length and a different time. So either way, the outcome is the same when you view it in, whether you view it in the frame of the evil professor who is smacking cleavers towards a snake for some reason, or the frame of the snake does not get cut. But what the snake sees, what I see as simultaneous events, the snake sees as different events that happen at different times and in fact even at different places. So then we want to look at how we add velocities because we know how to add velocities when we have moving coordinates or moving coordinate systems classically. We want to come up with something similar for relativity. So classically, if we have our stationary system S and our moving coordinate system S prime, this one's cooler, so they're going to wear shades. So those are supposed to be sunglasses. We can add the velocities as v prime equals v minus capital V, where this is capital V is the motion of the moving coordinate system. So now we have a particle which is going to be moving either at its position is either r of t or r prime of t. They are the same thing, but we are going to write them differently in different coordinate systems. The velocity is dr dt, which is the limit as delta t goes to, actually like this, limit as t2 minus t1 goes to 0 of r2 minus r1 over t2 minus t1. So we actually are looking at differences in times and differences in position. And we know how to do that because we have our Lorentz transformation. So dx prime is just gamma dx minus v dt. Dy prime is dy. Dz prime is dz. Dt prime is gamma dt minus v dx over c squared. So we can actually use a Lorentz transformation for these, for the numerator and the denominator, because this expression is linear. So then we get Vx prime. Here I'm going to take, that's gamma dx minus v dt over gamma dt minus v dx over c squared. And I'm going to divide through by dt, so these guys cancel out, and I divide through by dt on top and bottom. So I get dx dt, which is just vx minus v over 1 minus v times vx divided by c squared. Vy prime is dy over gamma dt minus v dx over c squared. Again, I'm going to divide through on top and bottom by dt, so I get dy dt over gamma 1 minus Vx over c squared. Vz has the exact same form, or Vz prime has the exact same form. And now I know how to convert a velocity in one frame to another. I can also switch the primes and unprimes and get the reverse equations as well. And a few things to point out here. So Vy prime is not simply Vy because it is actually dy dt, or dy prime dt prime. And we're taking something which varies with, we're taking the first three components of a 4 vector and dividing them by the fourth component, which is why it doesn't transform like a typical 4 vector. Also, I'd like to point out that this gamma is the gamma for the different coordinate systems and not the speed of the object in the coordinate system, whereas this is these are the components of the velocity of the object in the coordinate system. So now we have our velocity addition equations, and I'm going to leave them up. And we're going to do a couple of examples just to show how you add velocities and what the consequences are. So this is example 15.4. You add two velocities close to c. So we have a coordinate system moving at the speed of 0.8 c. And this has, then we have we are looking at an object in the unprimed frame, which moves at a speed of 0.6 c. And now we want to ask, in the primed frame, how fast is this object moving? So it is worth pointing out that classically, this would just be really easy. You add the velocities, and you would get that the velocity in the primed frame is 1.4 times the speed of light. Obviously, relativistically, that's clipping the edge of it off. So obviously, relativistically, that cannot be happening. So we have to use our relativistic velocity addition equations. We are lining them both up along the x-axis. So then so we can switch the prime and the unprime to get an equation which works. And then we also have to switch the sign of capital V if we're going from prime to unprime, or going from unprime to prime. So here we have Vx prime plus V1 plus Vx over c squared. And this is now a prime. So now this is 1.4c, what we would have classically, divided by 1 plus 0.8 times 0.6, and this works out to be 0.95c. So if I take two things that are moving relativistically and I add their velocities, when I add them relativistically, I do not in fact get above the speed of light. And you can see, so stare at this a while, you will see that you will never get a speed which is above the speed of light. It's a little trickier to see when you consider a velocity which might not be aligned with the moving coordinate system. But you will not get a speed which is above the speed of light. Now, we can look at example 15.5. Add two velocities, one of which equals c. So now we are going to make v prime equal to c, and we actually don't need to choose a capital V. So in the moving frame, the speed is the speed of light, and we will line it up along the x direction. So Vx is c plus capital V over 1 plus Vc over c squared. So we end up with c plus V over c times c. Here, let me write this out. A couple more steps. 1 plus, I'm going to factor out a 1 over c. First of all, one of these guys cancels out, so I get a 1 over c times c plus v. So I am left with 1 over c, which is just c. So when one of my velocities is c, when I have an object which has a velocity of c, it will have a velocity of c in any other frame. And then we can look at what happens when you have a velocity which is very low compared to the speed of light. So if Vx is very small, then we have, let's just look, so Vx prime, if Vx and capital V are very low, this thing becomes roughly 1, and you are left with Vx minus V, Vy here. This term is roughly equal to 1, and this term is roughly equal to 1, so you end up with Vy prime is roughly equal to Vy, and Z prime is roughly equal to Vz. Now we're going to take this and put it in a vector, and we're going to add space and time together. So we've talked about a Lorentz transformation, and when we wrote down the Lorentz transformation, it looked an awful lot like a matrix, and it looked an awful lot like you could take time and space and put them in one vector and call them all a vector, which is transformed by a matrix when you do a Lorentz transformation. And that is exactly what we are going to do. And we are going to call time the fourth dimension. And that because time is now mixing with space, and space is mixing with time. So before we dive into that, we're going to do a little bit of what may or may not be reviewed, depending on your background with linear algebra, and talk about what happens with three-dimensional space. This is either the first time that you've seen it, or it is a review. So we can take some general vector, and we've actually kind of already done this. When we talked about generalized coordinates, it's a little familiar. We can take any vector and write it in terms of basis vectors. You're used to doing this where our basis vectors are x hat, y hat, and z hat, except that now I am going to be a little more general. and I'm going to call them E hat 1, E hat 2, and E hat 3. And we've even done something where these are not, strictly speaking, the Cartesian coordinates, because when we use spherical polar coordinates, we use r hat, theta hat, and phi hat. R hat, phi hat, and theta hat. So this is just saying that if you have a complete set of basis vectors for a three-dimensional space, you need 3 vectors, and they have to span the space, the 3 different dimensions. You often choose them to be perpendicular, but they don't have to be perpendicular. And you're going to write you can write any vector as a sum of components written in terms of each of the different basis vectors. So this is analogous to taking some arbitrary vector and breaking it down into x, y, and z coordinates, which you can always do. And we can then write this as, in a different way, the sum from I equals 1 to 3 of the qi e hat I. So we have the 1, 2, and 3 components of the vector. And we can also note that qi is e hat I dotted with the vector q. We will rename the vector r, which was our x, y, z, and we will just call it x vector. This also echoes some of the language in other textbooks. All right, so we have chosen one set of coordinates here with one coordinate system. And we can always, physics is independent of the coordinate system, so we can always redefine this to be part of a prime system. So qi prime is e hat I prime dot q vector, which is e hat I prime dotted with here I'm just writing q in terms of its basis vectors, and I can rewrite this as e hat I prime dotted with e hat j I had to simply call this index j so that I wasn't repeating the index. And this sort of starts to look like a matrix element. Generally, if you're in this class, at least at our university, you are strongly considering graduate school, so we're not really going to back off the math. I'm going to be throwing matrices and complex numbers and differential equations at you like your pros, because you will be. All right. And we will refer to q as a vector. You can call, but we'll note it as a column matrix. Where a column matrix is basically just a vector, because a vector is a one-dimensional matrix. Then what we're really doing when we are converting, when we're going between q hat prime, or q prime and q, is taking Q, we're saying that Q prime is this matrix, which is E1 hat prime dot E1 E. Let's see, I'm going to have a bunch of E's and E hats. E's and E primes and E hats, and I'm just going to fill this in real quickly. And then we're going to go back and double check that we know which ones are 1s and 2s. Okay, my diagonals are easy because those are all the same index. And then I want my Q1, this first vector, to be E hat 1 prime dotted with each of the others. So the first one is always the row, and the second one is the column. Okay, so I can describe how I change between Q and Q prime as multiplying Q by a matrix. And we call this a rotation matrix. I'm going to call it R. And you can write any change of coordinate system with the same origin as a rotation matrix. So then we can do a simple example. And we are going to, I will use my colors here. X1, X2, no, so X1 and X3. And X2 doesn't change at all. We're rotating about the X2 axis. And we have X1 and X2, and this is an angle theta. So if I take some vector, I have some component of a vector which is in X1 direction, and my X1 prime is going to go like component is cosine X1 cosine theta plus and then there's going to be an X2 prime component, which is going to be the sine theta. So I will leave it as an exercise for the student to confirm. This is cosine theta, sine theta, 0, 0, 1. We don't change the second axis. And here we can, so then we can write the X1 prime. Let me actually do this, writing it as a matrix. So X prime is cosine theta, 0, sine theta, 0, 1, 0, negative sine theta, 0, cosine theta. X1, X2, X3 And this tells us that x1 prime, x2 prime, x3 prime are all equal to x1 cosine theta plus x3 sine theta, x2 negative x1 sine theta plus x3 cosine theta. So you can check that if theta is 0, then you get x1, x2, x1 prime equals x1, x2 prime equals x2, x3 prime equals x3. And then if you rotate 90 degrees, then then this guy is 0, and all of you're basically just flipping x1 and, well, you're not quite just flipping them, because the x1 term the x3 term becomes negative x1. All right, and I will tell you, but we're not showing it here, that you can write any rotation as some product of these matrices. And if you're rotating by arbitrary angles, then these matrices get really, really ugly, but you can at least do it. Now, having these really ugly matrices is how you ended up with the really ugly formulas in the section on arbitrary rotations of bodies, where the Euler equations were really pretty gnarly. So here you see that the reason for listing this as a vector is that actually you end up getting mixing between x1 and x3, and we have the same sort of argument for a Lorentz transformation, that you end up mixing the different coordinates, and you end up mixing the coordinates with time. So with that, we are going to start describing Lorentz transformations as rotations of space-time. And we are going to start by defining x, and we're going to specifically use x with the vector symbol as x1, x2, x3, just the spatial components. X without the vector symbol is going to be the 4 vector. This is not the world's best notation, but you sort of run out of primes and unprimes and different variables, so we're kind of stuck with a variety of different limited choices. And then here we're going to put, for the 4th component, CT. And I want to caution you here that there are a variety of different ways to come up with with notation for 4 vectors, and different textbooks use different notations. Sometimes you have an I here, and that changes what you have for the Lorentz transformation. So, and sometimes you change the sign there, so it's negative, so you may have plus or minus I, or not have an I, and it's going to change how you write some of the notation. So I guess what I would say is, do not blithely change books. If you change books, you have to be careful, because upon occasion, because you could end up with just completely wrong notation. You can't, you have to use a definition of x which is consistent with the book that you are using. So then we can write x prime not with the vector symbol, so I'm talking about the 4 vector, as x1 prime, x2 prime, x3 prime, and x4 prime, where here x4 is CT, so x4 prime is CT prime, and this is equal to gamma x1 minus gamma beta x4 x2, x3, negative gamma beta x1 plus gamma x4. And this is equal to, I will come back to how you can define this. We can define an angle, phi, so that this is cosh phi times x1 minus sinh phi x4 this is simply x2, x3, and this is negative sinh phi x1 plus cosh phi x4. And the reason for writing it as an angle is that you would notice that this starts to look kind of similar to our rotation matrix. So if we define, just to elaborate on this a little more, if we define cosh phi to be gamma, this is 1 over 1 minus beta squared. And we have an identity similar to, you all almost certainly were exposed extensively to trig identities. There are analogous identities for hyperbolic functions. They have echoes of what you have for trig identities, but sometimes there are sign differences, so proceed carefully. So here, this is the same way that you have cosine squared plus sine squared equals 1. Cosine squared minus cosh squared minus sinh squared is equal to 1. And it sort of makes sense that you would have a lot of similar identities because Euler's equation relates sine and cosines, exponentials of functions to sines and cosines, and these are exponentials, and they correspond to sines and cosines with imaginary, with complex numbers. Okay, so here we're then going to use this identity. Cosh squared phi is 1 over 1 minus beta squared. So I've just squared this. And this is 1 plus sinh squared. I dropped the squared there. And so then I am going to take this and write this as 1. Then I'm going to write this. I'm going to put the 1. I've got sinh squared phi equals 1 over 1 minus beta squared minus 1, which I will write as 1 minus beta squared over 1 minus beta squared. Well, this leaves me with a 1 minus beta squared on the bottom, but now I have 1 minus 1 plus beta squared, so I have a beta squared, and this is equal to beta squared gamma squared. So sinh of phi is equal to beta gamma. So beta gamma is sinh of phi, and gamma is cosh of phi. And that is how I get, how I can write this with coshes and sinh. So we will introduce just a little bit of extra notation. So we are going to then call this 4 vector XCT. So sometimes we may not want to write x1, x2, x3. So it is the x vector, the 3 vector, plus this time component. And we can write, we'll write any vector, any 4 vector, as Q4. So this is the spatial component and this is the time component. And we are going to assume that these are column vectors. If we want a row vector, we have to take the transpose. We can then write our Lorentz transformation as, we'll use this lambda. It is gamma 0, 0, negative gamma. And again, read your books if you're switching between books. Read your books very carefully because they use different notation. There are tomes written on why certain approaches are better, but they are all equivalent. What matters most is that you are consistent. And so this is our Lorentz transformation. And then we can write x prime is the Lorentz transformation of x. This is not the most general. We're dealing with a transformation where, first of all, you're keeping the origins the same, and second of all, you are only putting the coordinate system is only moving along the x direction. If you wanted to have velocity in multiple directions, you can have notation where you have actually the multiplication of multiple different Lorentz transformations. What you would have to do then is, so here this is the velocity along the x direction. If you want the velocity along the y direction, your gamma, and you would have to switch the rows and columns for x and y. You should always end up with a symmetric matrix. For if I wanted to come up with one where you're moving along the y direction, let me just do it for you. So first of all, I'm going to have 1, 0, 0, and because I have no mixing in the x direction and I have no mixing in the z direction, so I have 0, 0, 1, and I'm also going, I did 0, 1, 0 because I still get mixing with time, and here I have zeros, and now all of my mixing is between y and time. And so here I would have gamma, and negative gamma beta, negative gamma beta. And if I wanted to find the matrix which for a boost along the z direction, I'm going to have 1, 0, 0, 0, 0, 1, 0, 0. Here I have zeros. I have no mixing of x and y together. Here I have a negative gamma beta, and here I have gamma, gamma. Now, if you had boosts, which is what is meant by saying motion in one direction, in the x, y, and z direction, so it's all just moving, so you have coordinate systems, the prime coordinate system is moving in all 3 directions, you would have to multiply 3 Lorentz matrices, and the gammas and the betas would each be different because it would be for the boost along each direction. So more generally, you would have, so any transformation is going to be either a pure boost, which would be along one direction, or a boost, which would be potentially the product of these three, as well as a rotation. And the transformation for a rotation, we can write it as this matrix R and 1. So just rotating the coordinate systems without having any relative velocity is not going to change the time direction. When I don't write the extra zeros, I really just mean you can think of it as filling it in everywhere else. But that would be just your coordinate transformation that we had in 3 dimensions with the sines and the cosines, and then no change in time. So a pure boost in an arbitrary direction would involve a couple rotations plus a boost. The easiest way to do it is to rotate so that the velocity of the coordinate system is lined up with x1, and then do a straightforward boost, and then rotate back to the previous orientation. Any Lorentz transformation, everything I can come up with, which is a Lorentz transformation, can be written as the product of a rotation plus a boost. And this would be a rotation, and these guys would be boosts. A 4-vector is anything which transforms in the same way as the space vector under all Lorentz transformations. So a 4-vector is any vector, let me actually put it as Q. It is any vector for which Q prime is lambda Q for an arbitrary lambda, for an arbitrary Lorentz transformation. And we will define a 4-vector as the vector where each of the terms, so a Q is a 4-vector. Actually, I should not put the vector sign because it's now a 4-vector, where this is Q1, Q2, Q3, and Q4. Where the values transform under this type of transformation. We will see other 4 vectors than just position. So we have momentum, but we're going to have to tweak our definition of momentum. And if we write a law in terms of 4 vectors, we can check whether it holds relatively easily. That does not guarantee that the law is true, but we will demand that it is at least the same in all frames. That is, that we say that the laws of physics must be true in all frames. So if we have a law of physics and we transform it, it must be the same in all frames. So then we're going to define a few more terms. A quantity which is invariant under rotations, meaning that you are just changing the spatial components and just changing your definitions of those spatial components, is a rotational scalar or a 3-scalar, meaning that it is scalar. It stays the same even if you're just changing the spatial time determinations. And examples are mass and time. A quantity which is invariant under Lorentz transformations is a Lorentz scalar or a 4-scalar. Examples are mass, but we're going to have to be careful about how we define mass, and not time. So time is explicitly not a 4-scalar. Now, if all we're doing is rotating coordinate systems, the length of an object is constant. We will see that we can come up with an equivalent of, we have an equivalent to a length for, which is the part that includes this time factor that ds squared, that is a 4-scalar because it is invariant under a Lorentz scalar. And then we're going to look at the invariant scalar product. So just like we had a dot product, we're going to come up with the equivalent. And we are characterizing transformations by the things that they leave invariant. So in 3 space, we have the length, and I will note some books use s squared. This book uses s, is x dot with itself, and this is x1 squared plus x2 squared plus x3 squared, and if we change coordinates, it is x1 prime squared plus x2 prime squared plus x3 prime squared, and this is a 3-scalar because if we rotate the coordinate systems, we keep the length of the object constant. Then we want, so if we have 2 vectors, and x is vector A plus vector B, where A and B are any other vectors. If x prime is A prime plus B prime, so in the other coordinates. So these are just the rotated vectors x, A, and B. If we simply consider spatial rotations, x prime, or let's see, x dot x, which is s, is equal to a dot a plus b dot b plus 2a dot b, and this has to equal x prime dot x prime. So it is a prime dot a prime plus b prime dot b prime plus 2a prime dot b prime. Now, these A and B are 3 vectors. So this is also equal to A prime dot A prime, and this is equal to B prime dot B prime. So this term cancels out this term, and this term cancels out this term. So we are left with 2a dot b equals 2a prime dot b prime. Now, or a dot b is equal to a prime dot b prime. And if you go back to the geometric definition of the dot product, where it is the product of the magnitude of the 2 vectors times the sine of the angle between them, the cosine of the angle between them. So then all you're doing when you're changing coordinate systems is changing the basis vectors. You're just writing the vector differently, but you're not actually fundamentally changing what the vector is. So if I have 2 coordinate systems, and this is my unprimed coordinate system, and this is my primed coordinate system, and then I have some vector A, and I have a vector B. When I rotate coordinate systems, I'm not changing A and B. I'm changing the breakdown of A and B into different components. And so AB times the cosine of the angle between them will still be the same. So I have to have the dot product conserved under transformations. So the scalar product, if we have that, so because the length is constant under rotations, the scalar product is also invariant. So now we are going to define the equivalent for Lorentz transformation. So we are going to define S relativistically to be x1 squared plus x2 squared plus x3 squared minus x4 squared. So this looks very similar to the length, but it's not quite. And this is the distance squared minus c squared t squared. And yeah, some books call this s squared and not s. I will follow the book, even though I prefer s squared. And now we will prove that it is invariant. And we will use the Lorentz transformation to prove that it is in fact invariant. So we're going to flip back to our Lorentz transformation. And write S, we're going to start by writing S prime and show that it is the same thing as S. So x1 prime is gamma x plus v t, and then we square it. x2 prime we square, but it doesn't change. And so x2 prime is x2, and x3 prime is x3. So we have an x2 prime squared, or sorry, an x2 squared. I keep wanting to put a prime up there. x2 squared plus x3 squared. And then we have minus c squared t squared. And t squared is gamma squared t minus v x, and this actually should be an x1 over c squared. And yes, I have written this slightly differently from in my notes because I like living dangerously. So here I have gamma squared x1 squared plus gamma squared v squared t squared plus x2 squared plus x3 squared minus c squared gamma squared, oh, this has a square, t, I forgot my cross terms, foolishly enough. Here I have a t squared, and then here I have a minus a v squared x1 squared over c to the fourth times gamma squared c squared. Here I did not write my cross terms, gamma squared x1 vt, there's a 2, this is a plus, and then I have minus a minus no, I have a minus this has a sign error. So this has that sign, and then this cross term, which I thus far left off, has minus a minus or a plus c squared gamma squared. There's a factor of 2 because it's the cross term, capital V x1 over c squared t. And we can now take it upon ourselves to simplify. And here, the c's cancel out. I am left with these two terms canceling out. And I can collect some like terms. Let's see, this term, this has units of length, and yes. So I will, my x1s look like this. I have gamma squared, and then let me collect, so x1, I have a gamma squared, x1 squared, I have these two terms. We're going to pull the x1 out. x1 squared. There are gamma squareds everywhere. I have a 1 minus. And then here, this is v squared over c squared. So it is beta squared. My x2 terms are simple. My x3 terms are simple. And then I have plus t squared gamma squared. And then c squared. I'm going to pull a c squared out. And this leaves me with beta squared minus 1. I should have a, except, yes, that is equivalent to minus a 1 minus beta. And now we look at gamma squared times 1 minus beta. So gamma squared times 1 minus beta squared is 1 over beta squared times 1 over 1 minus beta squared times 1 minus beta squared, which is just 1. So all of this simplifies to x1 squared plus x2 squared plus x3 squared minus c squared t squared, which is simply s. So that was a lot of dumb algebra, but it showed that s prime and s are equal. So we will call it the invariant length, and the invariant length is invariant under a Lorentz transformation. We will then define something that we will call the invariant scalar product, which is going to look a lot like the invariant length. The invariant scalar product, x dot y, is x1 y1 plus x2 y2 plus x3 y3 minus x4 y4. So for any four vectors, this will be our invariant scalar product. And the invariance of x dot y is a property of Lorentz transformations. So x prime equals the Lorentz transformation of x, so y prime is equal to the Lorentz transformation of y. And here, x prime dot y prime is the dot product of ax with, or sorry, I keep, my notes have it a, I keep wanting to write an a, but it is a lambda. So it is the dot product of lambda x and lambda y. But this is simply x transpose lambda transpose lambda y, which is x dot y, because this is equal to 1, or to the identity matrix. Here I'm relying on a little bit of matrix algebra that I have not explicitly shown. So a transpose is when you flip the rows and columns. So if you have a column matrix, when you make it when you take the transpose, you have a row matrix. When you have a Lorentz transformation, we have written our Lorentz transformation as gamma 0, 0, negative gamma beta 0, 0, negative gamma beta 1, 1, 0, 0, 0, 0, 0, 0, gamma. So this is our lambda. And I am going to take the transpose of it. That means that I'm going to flip the rows and columns. Now you will notice that the diagonal stays the same, gamma, and then this guy stays the same. So if I flip the rows and columns, this is actually the exact same matrix. Now, when I take the product of, so I can also call this lambda transpose. When I take the product, lambda transpose times lambda, here I am going to get a gamma squared, here I drop my gamma, times 1 minus beta squared, but I just got done showing that that's just 1. And here I have 0 because these are orthogonal, and down here I have a negative gamma squared beta, and let's see, this needs to be here. These should have opposite signs. I have a gamma squared beta, and here, this is where the other notation with i's works better. So here, the if I actually want to take the inverse, I also have to change the sign. So if I had used imaginary numbers for my time component, I would have gotten it naturally. And here I sort of have to add it in by hand, that these, if you do two Lorentz transformations, they will cancel out. So lambda inverse is actually not lambda transverse for this particular definition. And this is why I should not fly without a net. But basically, when you do the lambda transformation forwards and backwards, you end up getting the same, you end up getting the identity matrix. So given the current notation, the part that I could not have assumed was this. But it really is a lot nicer if you have that imaginary part of the time so that you can get away with that. All right, so then this scalar product is invariant, and you can imagine flash from a light bulb, and the distance traveled is r squared, which is c squared t squared, and that means that this is 0, and in other words, the position of the wave front x dot x is 0. You can imagine this as like light spreading out from, imagine a flashbulb at the origin, light spreads out at the origin, and the distance is r squared, and r squared minus c squared has to equal 0 because that's the front of the wave, that's the wave front. Now, in a different frame, s prime, you still have light traveling at a speed of light c, and it is going to take the same shape. So r prime minus c prime t prime squared, c squared t prime squared is also going to be equal to 0 because the wave front is spreading out. So a spherical wave in S is also a spherical wave in S prime, which is a reflection of the postulate that the speed of light is constant. So then we're going to talk about something called the light cone, which is how it's going to help us visualize what's going on and how to divide space into different parts. Now, I cannot draw in 3D. The book has an edge on me because they have infinite time, but I also think that there is something to be said for not having the best artistic skills. Maybe that's motivated by my lack of artistic skills. So we're going to put one coordinate. We will actually choose x1. The book draws it in 3 dimensions, and you have to at least drop something because you can't draw 4 dimensions. But I am going to draw it in 2 dimensions. And we have x1 and x4. So you can then draw different spaces. So we are going to draw this line. X1 equals CT. X1 equals negative CT. And then you can extend these. So this is time. Now this is only for one of our coordinate systems, and we're talking about transforming to many different coordinate systems. And in the forward light cone, that is in this direction, we get all points which could be visited by light from the origin in space-time. So imagine that you had something start here, a light flash. You could have light bouncing off of mirrors. You could have someone dancing, and you're able to see that. This region is the region which could be visited by light from this point in time, because light can never travel faster than CT. So you cannot reach, if you're here, there is no light which could reach you from this point. But if you're inside here, it is possible. The backward light cone is all points where light could come from. So if you're here in space-time, you could get light from these events, but it's not physically possible for you to get information about what was happening over here. Since X4 is CT, you see that this line, which is the line between the absolute future and the absolute past. So this line makes a 45-degree angle with the axis. Observers will always agree on which things are part of the light cone. They won't agree on which things happen first and which things happen last when you're in here, but they're going to agree on where could light here have come from, or images or information, and where could light from here go to. They will agree on that, even if they don't agree on the slope or the shapes here. So you can imagine in the interior of a light cone that you have a point P. And so we're going to have absolute past, absolute future, everything else. So imagine a point P, which is here, and it is inside the light cone. That means that T is greater than 0, and that R squared is less than, it's inside, so it's got to be less than C squared, T squared. This one means that X4 is greater than 0 because T is greater than 0. And then this means that X1 squared plus X2 squared plus X3 squared is less than X4 squared. So the point P must have occurred after the time at the origin. Now, we don't know how far after. That is going to depend on your frame of reference, but all observers will agree that this has to be after the origin. And then this means X1 squared plus X2 squared plus X3 squared minus X4 squared is less than 0, or X dot X is less than 0, which means that S is less than 0, which means that S prime is less than 0, because S is invariant under a Lorentz transformation. So if P is in the forward light frame, is in the forward light cone, in this coordinate system, it must also be in the forward light cone in every other coordinate system. This is why we call it the absolute future. Similarly, if an object P is in the past, you would simply flip, ooh, that's not a good color. That's not my nice contrast. You would flip these guys. But the argument holds even if you flip the sign, whatever it was, if it was in the past in S, for all other frames, it must also be in the past. So this part we call the absolute past. We could move the center of the light cone, but this is always going to be in the absolute past. And in the exterior of the light cone, we are going to have space-like vectors. So we're going to look at a point P. And now I'm going to move my point P to match figure 15.9. But P is still going to be at X, CT. And it is outside the light cone, and we will call this Q, the point that we want to investigate. We could move it around. So XP minus XQ, quantity squared, is greater than C squared TP minus TQ, quantity squared. So this, we can write XP, now this is the 4 vector, not the 3 vector, minus XQ, quantity squared, has to be greater than 0. So if P is outside of the light cone from Q, then all observers will see it remain outside of the light cone. So we have a proposition that you let P be any given space-time point outside of the light cone of a given second point Q. There are frames where TP, the time of point P, is greater than the time of point Q. There are also frames where the two times are equal, and there are also frames where the two times are, where the time of P is less than the time of Q. So if you have a point outside of the light cone, you cannot say something about the ordering. And this has profound implications for causality, because I can never travel faster than the speed of light. So an event here cannot be caused by an event here. Now, whatever happens at this point in space-time could be caused by something here, or here, or here, or here. But something happening here cannot be caused by something happening here. And you will hear about these causality arguments in various fields of physics. It's actually come up in my field of physics, where we talk about it is not possible for these particles to be correlated with each other because they cannot be causally connected, because you could not get light from from this region of space to the other. It's physically impossible. So if P is outside of the light cone for Q, then it is ambiguous which happened first, and they cannot be causally connected. And because any signal between P and Q would need to move faster than light. We call this space-like. So because x dot, I keep wanting to make it a derivative and not a dot product, x dot x is greater than, or sorry, x vector dot x vector is greater than c squared t squared. This means that x4, if we put it all along one direction, we're going to choose to have only the x1 equal, or sorry, x2 equals x3 equals 0, just to make life a little bit easier. So x4 is less than x1. So we can always find a beta, which is x4 over x1, because that will be less than 1. And we can shift coordinates in order to get x to be x1, 0, 0, x4, so that we only have we can choose to have a coordinate that then this ends up with only a spatial component. There is always a transformation which will allow you to have only a spatial component, which is why these are called space-like points or space-like vectors. Conversely, if you are inside the light cone, so we're going to just be lazy and move that there. Then there is, you can always write the position vector as 0, 0, 0, x4. You only have a time component. You are then looking in, you are at the rest frame of that particular point. Oh. So in that case, everything is time. Whatever this is, you are in the rest frame of that particle. And in that case, dx equals 0, dx is 0, 0, 0, ct, dx squared is v squared minus c squared. This should be, yes, and then this has got to be less than 0, and you get v squared less than c squared in all frames. So there are 3 places where the speed limit came up, where the speed of inertial frames has to be less than the speed of light. And in any inertial frame, the speed of a causal frame has to be less than the speed of light. And in any frame, the speed of a particle has to be less than the speed of light. So our speed limit has come up repeatedly. All right, so now we need to think about what exactly we mean by a 4-vector and what is a 4-vector. We're going to be going through something called the quotient rule. So first of all, we can always put together a collection of 4 numbers. But these numbers are not necessarily a 4-vector. Because they don't have to transform with the Lorentz transformation. So how do we know that something is a 4 vector? We're going to allow x to be a 4 vector. So x is x1, x2, x3, and x4. Let's say that we have a number phi, which is k dot x, or k1x1 plus k2x2 plus k3x3 minus k4x4. And let us suppose that this has the same value in all frames. So it is phi is a 4 scalar. Then k is a 4 vector. So if phi is a 4 scalar, then this is also equal to k prime x prime, which is equal to k prime lambda x and lambda, well, this has to transform as if the two components were transformed with a Lorentz transformation. So I must be able to replace x prime by lambda x and k prime by lambda k. And that means that k prime has to equal lambda k, which means that k prime has to transform through a Lorentz transformation. Therefore, it must be a 4 vector. And this property that if something, if the dot product of, if this quantity is equal to a 4 scalar, that k has to be a 4 vector, is known as the quotient rule. Because you can, of course, write this as a quotient. K prime is you can, of course, write it with a quotient. All right, so then we're going to use this to turn to the Doppler effect. So the Doppler effect is a shift in the apparent wavelength or apparent frequency of some wave when the source or the receiver is moving. So classically, a lot of the introductory textbooks talk about they distinguish between whether the source of the wave is moving or the receiver of the wave is moving. You guys are big physicists now, you're upperclassmen, and you know that there's actually no difference between the source moving and the receiver moving. What really matters is the relative velocity between the source and the receiver. Okay, so I like to conceptualize the Doppler effect as if I like to imagine the peaks of the wave as if I were throwing marbles at someone. So if I am running towards you throwing marbles at a rate of 1 per second, because I am running towards you, they are going to hit you faster than 1 per second because I'm moving towards you at the same time. So if I am running towards you, the frequency increases. Now the frequency of a light wave corresponds to its wavelength. So if the frequency increases, then that corresponds to moving towards the blue. We call it blue shifted. If I am running away from you while I am throwing marbles at you, then if I'm throwing marbles at a rate of 1 per second, then you will get them at a rate which is lower than 1 per second. So the apparent frequency decreases. This is a red shift. And there are lots of effects that happen because of Doppler shifts. So if you have laser light, so you can have laser light, which the shift when you have a moving source or receiver can lead to Doppler cooling. The Doppler shift is actually used in radar when the police measure your speed with radar, and when we talk about relativistic Doppler shifts, we actually can measure the speed at which some stars move relative to us by looking at the Doppler shift, because we know that certain atoms absorb and emit certain wavelengths, and we know the actual wavelengths. So if we see that the pattern of wavelengths is either consistently shifting to higher frequencies, we say that it is blue shifted. Consistently shifting to lower frequencies, we say that it is red shifted. So then we want to quantify this. We're going to look at a plane wave. And a plane wave can be described as having some amplitude, cosine. This is not the same k as before. Well, it could be. It's an arbitrary vector, and these are three vectors. The k dot x minus omega t minus some phase shift delta. So this could be a pressure wave or a sound wave, or more interesting to us, a light wave. And for a light wave, this would actually be the amplitude of either the electric field or the magnetic field. K is the wave vector. Delta is the phase shift. X is the position in space you're looking at. So you're describing the amplitude of the wave as a function of the position in space. And that amplitude could be E or B or pressure. So then we have several relations which are useful. The magnitude of the wave number is 2 pi over the wavelength. The angular frequency of the wave is 2 pi times the frequency. This book uses nu for a frequency. When I'm writing a nu, I distinguish it from my v's because my arms on my nus are curly, and when I write a v, it is straight. Over the years, I have developed a certain style so that my Greek letters are distinguishable from my Roman letters. All right, and then we are going to consider a source. We will have this be someone, my son, is riding on top of the coal tender for Big Boy 4014, and I'm sure that I will get critiques because I've definitely put the wrong number of wheels on this. And so this is the Union Pacific Big Boy 4014, and my son is there. It is moving at relativistic speeds. Well, okay, it actually really wasn't the fastest locomotive. The fastest steam locomotive was the Mallard, everybody. But we're going to pretend, because it makes the problem more interesting, that it was Big Boy 4014. And it is moving with some velocity, capital V. This is now our coordinate system, and he shines a laser at an angle here, and he's trying to play with our cat. So this is our cat, Minda. He shines a laser so that she chases the cat, the laser. She's kind of a lazy cat. She's very particular. So there, this is Minda chasing the laser. And the question is, what color of light does Minda see? So we will look at k dot x minus omega t, which is just k dot x, the 4 vector k dotted with x. Now, I have to argue that this vector k is actually a 4 vector for my proof to be able to work. So think about this as describing the position, the relative, it describes the position of the wave relative to troughs or crests of the wave. So where you are relative to a trough or crest, because this whole thing is the total phase. So this is where you are relative to troughs or crests. And that has to be the same in any frame. So this has to be a 4 vector. And so we will, that 4 vector k is then the 3 vector k combined with omega over c. And this is so that when we take the dot product, we get that. So we will assume that we have light from the moving coordinate system emitted at an angular frequency omega naught. And then we can look at the Lorentz transformation of k into of k prime into the prime frame, unprime frame. So k4 prime has to equal gamma k4 minus beta k1. And this is simply because if we have, if this is a 4 vector, it transforms with a Lorentz transformation. And now I'm going to use another couple identities. I'm going to use k4 equals omega over c, and then I can get, so the useful, just rearrange this, c equals omega over k, or the total magnitude of k equals omega over c. K1 is going to be the magnitude of k times cosine, that cosine of theta. And then here I've said that k has to be omega over c. So this is omega over c cosine theta. So then I can rewrite this equation. Only I'm going to replace my k4. K4 is omega over c. So I'm going to replace k4 and k4 prime by omega over c and omega prime over c. So omega prime over c, which is omega naught, the angular frequency in the moving coordinate system over c. And this is just gamma. And this is the omega over c. This is the omega that I observe, minus beta omega over c cosine theta. So here I can get rid of, I could multiply through by c, and I want to solve for, I can then write this as omega, there's gamma omega 1 minus beta cosine theta. So I get omega equals omega naught over gamma 1 minus beta cosine theta. All right, so this is my result, and this is the useful one. Now, I want to compare this to, real quickly, to the classical Doppler shift. The classical Doppler shift says that omega equals 1 plus the velocity of the receiver. I've then divided through by c on top and bottom, or 1 plus the velocity of this, 1 plus the velocity of the receiver over the speed of the wave divided by 1 plus the velocity of the source over the speed of the wave times the initial frequency. Now, this is assuming that your receiver is moving along the direction of motion. So that is selecting theta equals 0. For theta equals 0, you get omega naught over gamma times 1 minus beta. And for non-relativistic speeds, we have gamma equals 1. So actually, let me put that down here because we're really looking at gamma equals 1, theta equals 0, and we get omega equals omega naught over 1 minus v over c. Up here, we are going to choose the receiver to not be moving and only the source is moving. The speed is then omega naught over, and then because of the source in the frame of reference of the receiver, the source's velocity is a negative v over c. So here, then I get the same answer classically. So we're happy with that because I should always get the same thing classically that I had. If I take my relativistic expression and look at low speeds, I should get my classical answer. Now we will go through a variety of definitions. We are trying to choose things which leave our physical laws roughly in the same form we're familiar with and are actually useful definitions. In principle, we can choose things to be anything we want, but we want them to be kind of similar to what we know. And we're talking about things like for velocity, for momentum, mass, and we're going to try to make a useful choice. So let's start with mass in relativity. And it's important to note that there are actually two definitions of mass in relativity. By far the most common one used is the rest mass, which is what something would weigh, what something's mass would be in its rest frame. But there is also the variable mass, so we have the invariant mass and the variant mass, where the invariant mass is much more popular. And so then the definition of the invariant mass is whatever you would measure the mass to be in its rest frame. As a practical matter, this is not necessarily that straightforward because you would have to take something and measure its mass in its rest frame, but we can usually extrapolate back to what its rest mass would in fact be. Now, we want to also define the proper time of a body. So if you take some object or person, it can be really anything, it is going to trace out a path, which is its position and its time. And this is its world line. So there is a frame where the separation is purely zero and its position, where the position is purely zero, the space-like part is all zero, and therefore you can write its world line as simply time. And if you do this, then in this frame, now this we call its rest frame because the object is always at the center of its world. It's always in the same spot at the origin. Now, you can take this and always transform the frame of the object to transform the position of the object to something else, to any other frame. And here, you will get that the 4 vector squared is just going to give you, so the position, dx is going to be v dt times c dt. So I can square this, and I can look at in its frame and in any other frame. And I can solve this and get that dt naught is 1 minus v over c squared, square root of that, dt, or that dt naught is dt over gamma. So this is the proper time, and this is any time. This is a Lorentz scalar. So we don't agree on the time, but if I ask you, if I measure your proper time, and you measure your proper time, we will get the same answer. It's sort of like we can define the rest mass to be the mass that you would measure in the frame of an object, and you're always going to agree that the person would measure the same mass. The proper time is the time that you will measure in the frame of the object, and everybody will agree that the object has the same proper time. So this is a Lorentz scalar, which is quite useful. And I think I actually forgot to mention that the mass is a Lorentz scalar itself. All right, and we want to revisit velocity. So we talked about how to transform the 3 velocity. But when we were talking about velocity, we were talking about dr dt. And this is particularly gnarly to transform because this is a 3 vector, and this is the 4th component of a 4 vector. So we are taking the ratio of these things, and it gets ugly. So we want to try to choose a vector which actually transforms like a 4 vector. So we're going to try something slightly different. Rather than choosing the ratio of a 3 vector to the 4th component of a scalar, which is what physically makes sense to us, it's what we'd measure, but we will take the ratio of a3 vector to a Lorentz scalar, because the proper time is in fact a Lorentz scalar. And we are going to call this u to distinguish it from the velocity v. The velocity v is what you would measure. And we will construct a vector which is dx. I will posit that this is a 4 vector. It is dx, the 4 vector, to dt. So now I have taken a 4 vector and I have divided it by, or sorry, dt naught. I have divided it by a Lorentz scalar. So this transforms with a Lorentz transformation, and this is constant with that transformation. So this is now dx, because we have decided to call the position x and not r, dx dt naught, c dt dt naught. So now that fourth component is not actually constant. It changes with, it can change with time. All right, so now we have the ratio of a 4 vector to a 4 scalar, so it is in fact a 4 vector, and we are good. Now, we will use dt naught equals dt over gamma, and we can then write that u is gamma dx dt c dt dt, or gamma, the velocity, our familiar friend, c. And then this is the 3 velocity. And the 3 velocity, so with this definition of our 4 velocity, the component of the 3 velocity is not, the component, spatial component of the 4 velocity is not the 3 velocity, but the 3 velocity times gamma. However, we want this to have the property of speed when we are, we want to have it look like our velocity, which is non-relativistic, when you are not relativistic. And we can see that in fact, so for non-relativistic speeds, this is 1, and we in fact get back to something which is non-relativistic. We also need a definition for relativistic momentum, and we want it to agree with our classical expression that the momentum is equal to mv when we are at non-relativistic speeds. And then we have a choice. What else do we want to carry over? We would probably like conservation of momentum to carry over, because this is a really useful tool. So let us try. So conservation of momentum would mean that the total momentum is conserved in all frames. So then we can ask, does MV work? It does not, because this is not conserved in all frames. This is left as an exercise to the reader. For the reader, that means it's really ugly. So instead, we're going to try a different 4 momentum. So we had the 4 velocity, and we're going to try the 4 momentum is just m times u, the 4 velocity. And that leaves us with gamma mv, gamma mc. And we will see if that works. And this means that the 3 momentum is gamma mv, or m times the spatial component of the 4 momentum. For a slow object, gamma is equal to 1. So this does in fact reduce to our classical expression, which is good. And then we now have that the conservation of momentum is the sum of the four momenta. So the sum of the four momenta finally in the final state is equal to the sum of the four momenta in the initial state. Note, I very specifically called them I and J because you could have different numbers of particles in different frames. Let me just leave that hanging there as a suggestion. So this makes relativistic momentum conservation look like classical momentum conservation. There are important differences between relativistic and non-relativistic momentum conservation. And let's see. So this definition, we will later see that gamma MC is another way of saying that you have energy conservation, because we will see that gamma MC is equal to the energy over C. And so then our momentum conservation formula, when we write it with four momenta, our four momentum conservation also implies energy conservation in one law. And since P has to be a four vector because V is a four vector, and we have multiplied it by a four scalar. So a four vector times a four scalar has to be a four vector. And then because momentum is a four vector, that implies that in fact you must have momentum transform like a four vector, which means that if you have momentum conservation in one frame, that you have momentum conservation in all frames. Now, whether or not you have momentum conservation is an experimental question, because we posit that this should be comparable to momentum conservation non-relativistically. It turns out experimentally that in fact, yes, we do have momentum conservation when we use this definition of momentum. And this is related to the definition of mass. So we introduced the definition of invariant mass earlier, and we said invariant mass is the mass that you would measure in the frame of the object. And we hinted that there was going to be something that was a variant mass. When you're calling this, so when your definition of momentum conservation looks like this, you have a choice. You either choose to say that the velocity is in fact changing, or that the mass is changing. So here, this M refers to the invariant mass. So we have so far, just as a choice of definitions, said that the velocity is changing, but you could instead say that your mass is variant and your mass varies like gamma, which is a function of the velocity, times m, and then you would keep the same form of momentum conservation that you had classically. Your momentum is just m times the variant mass, or m of the variant mass times the velocity. This makes momentum conservation look like classical momentum conservation, but there are places where it falls apart. So for example, here, you then don't get a kinetic energy which looks like 1/2 m var v squared, and the force does not look like m var times the acceleration. So here, because we don't want this definition is somewhat inconvenient. And also, m var is not a Lorentz scalar. So largely, while you will see this definition in some textbooks, and you will sometimes hear people talking about the variant mass, for the most part, most people, most textbooks, and most contemporary literature refers to the mass as the rest mass. And the variant mass is largely an artifact of history. So then we come to the definition of energy, and we are going to choose to define energy to be gamma mc squared. Now specifically, this is going to be the kinetic energy plus the rest energy. And this is the same thing as the fourth component, the time component of the 4 momentum times c, which also means that we can now rewrite the 4 momentum as the 3 momentum, not our classical 3 momentum, but our relativistic 3 momentum, gamma m times u, where the derivative then is with respect to the proper time, not the time. All right, and then E over C as the 4th component. Now, for low energies, so gamma is 1 over 1 minus beta squared. And take a Taylor series, because most of the time in physics, when you have no idea what else to do and how to proceed, you usually can take a Taylor series. So if you take the Taylor series of this function, you get 1 plus 1/2 beta squared plus higher order terms. So if we want to look at the energy when we are at low speeds, we can use the Taylor series. And this tells us that the energy is approximately equal to m times 1 plus 1/2 beta squared times mc squared. Or sorry, times c squared. I put an extra m there. So this looks like mc squared plus 1/2 mv squared. Well, that looks pretty dang familiar. So this term is irrelevant classically because we always have an offset. Now, relativistically, that offset is no longer arbitrary. So to have the 4 momentum, you don't get to just choose any old energy. You have to have the energy that would make this the total energy. And that is, in fact, what is conserved. So then if you, but classically this is irrelevant, so if you imagine a classical collision where you have energy conservation, let's say you have A and B and they collide, if you wanted to write your equation for energy conservation using this, you would have MA initial c squared plus B initial c squared plus 1/2 A V A initial squared plus 1/2 B V B initial squared, all equals the same thing, but in the final state, it's going to just take me a little minute to write this out. All right, and then if you're talking classically, these terms cancel out on each side because the mass does not change. So you are left with what looks like your old familiar classical energy conservation, kinetic energy conservation expression. So then we can define, just to make, so this term looks new and so we're going to give it, we are going to define our energy we're going to define our energy to be gamma m, so energy equals gamma mc squared, which equals mc squared plus the kinetic energy. So that is how we're going to define the kinetic energy relativistically. And when we do that, our kinetic energy is equal to gamma mc squared minus mc squared, or gamma minus 1 times mc squared. So then we can also have inelastic collisions, so where the energy is not in fact conserved, and in this case this definition of kinetic energy, when kinetic energy is not conserved, that implies that in fact the mass is not conserved either. And we actually measured that mass is conserved. So what's going on here? The change in the mass in most cases is so small that it hasn't been seen before. So whenever you're looking at where physics breaks down, where our current laws of physics and our current understanding of physics breaks down, when you have a well-established law, if you are developing things that work in new regimes, you have to be consistent with what has been observed before. But sometimes it can be that you just couldn't measure it. So we actually do have small changes in masses, but they were never measured before because they were so small. So let's go back to our expression. So we can write energy conservation then with our new definition of kinetic energy as the total mass times c squared plus the total initial kinetic energy equals the total final mass times c squared plus the total final kinetic energy. So when kinetic energy is conserved, then the mass has to be conserved. But that also implies that when kinetic energy is not conserved, the mass is in fact not conserved. And you can write the change in mass, which is the final mass minus the initial mass, is equal to, let me make sure that I've got is equal to the initial kinetic energy minus the final kinetic energy divided by c squared. So here you can see why this gets hard to detect, because this is c squared. This is on the order of 10 to the 17th. So you're dividing the change in kinetic energy by 10 to the 17th. So in most cases, when you have small, in SI units, in most cases, when you have small changes in kinetic energy, you're going to have small changes in mass. So we can use, as an example, the Frank-Hertz experiment, where you have electrons scattering off of mercury atoms. And in that experiment, the change in kinetic energy is negative 4.9 electron volts. So how big of a change in mass is that? We are going to use electron volts and talk about electron volts divided by C, or for the divided by C squared for the masses. These are funny units. It is worth you getting comfortable with them because We high energy physicists use them all the time. You can always write them out in SI units, but then you tend to be working with incredibly large and incredibly small numbers, and it gets a little tricky. Okay, so then our change in mass is negative, well, in regular high energy units, this isn't too bad because we say negative 4.9 EV over C squared. Well, what type of unit is that? We can convert this. So 4.9 electron volts times 1.602 times 10 to the negative 19th joules per electron volt, and then divided by C squared, 3 times 10 to the 8th quantity squared, meters squared per second squared, and so here, this is going to give us a power of 10 to the negative 19th, and then this is going to give us a power, again, on the order of 10 to the 17th, so you get 10 to the negative 19th, and then minus 17, and work the numbers all out, you get 8.7 times 10 to the negative 36. So, and then you can double check your work. Here, if I say this is 10 to the negative 17th, 19 plus 17 gives me a 36, so that's about the right order. And I have to work out what all of the smaller factors are. But I get about a 4.9 times 1.6. That's where I get, and then divided by a 9 and times 10, so that's where I get the 8.7. Okay, and compare the mass of a mercury atom. Actually, let me write this in. So the mass of a mercury atom is 200.6 atomic units, which works out to be about 3.3 times 10 to the negative 25th kilograms. Oh, I dropped my units there. That's kilograms. So then the change in mass is going to be this divided by that, which is 2.6 times 10 to the negative 11th. So you're talking about 1 part in 10 to the negative 11th change in mass. This is undetectable. Chemical reactions also have a tiny change in mass. And if you have other reactions that are, so nuclear reactions will often lead to a large enough change in mass that it is detectable. So if you have a neutron hit uranium-235 and it leads to the breakup of the uranium nucleus into krypton and I think that's barium, plus 3 neutrons, then the change in the kinetic energy in this case is 200 MeV, so that's times 10 to the 9th, and the change in mass divided by the initial mass is about 1 part in 1,000, and this reaches the point that you actually can detect it. So if we look at this mass energy in a little bit more detail, we have the 4 momentum is the 3 momentum, though note that that is our definition of the 3 momentum, which is not just mass times velocity, our classical velocity. And then the 4th component is energy over C. When we talk about energy over C, when we dealt with energy classically, we could always have an offset. There was an arbitrary offset. When we deal with this relativistically, that is no longer true because we expect it to transform with a Lorentz transformation. And our Lorentz transformation is given by this matrix. So if we take lambda p, we are going to get, so we're transforming from one frame to the other. We're going to get as our 4 vector gamma p, so we'll call this p prime is gamma p1, and then p2, p3, I have dropped off gamma p1 minus beta, gamma beta E over C, and P2, P3, and then the fourth one is negative gamma beta P1 plus gamma E over C. So now when we transform this with a Lorentz transformation, if we added a constant, it doesn't just, when we were dealing with classical equations, if you added a constant, it was totally arbitrary. You ended up with, you were only using the absolute, you were only using energy for energy conservation. The absolute shift didn't change anything, because you were always looking at energy differences. Now, when you are transforming your momentum with a Lorentz transformation to change the momentum from one frame to the other, if you were to change your energy by some arbitrary offset, you're going to change the first component of the momentum and the fourth component of the momentum. That is, that arbitrary offset isn't arbitrary anymore. It's changing everything. So you no longer have the freedom to define energy within an arbitrary offset. That specific energy really matters. So that is another way of saying that if you add some arbitrary offset to the energy here, it's no longer a 4 vector. And we need it to be a 4 vector because we need it to be transformed under a Lorentz transformation so that when you talk about energy and momentum conservation in different frames, our laws of physics hold, that we keep energy conservation, we keep momentum conservation. And then it's important to note that even at rest, even where gamma equals 1, because energy is mc squared plus the kinetic energy, even when the kinetic energy is 0, you still have some rest energy. And those are all important points to make. And then we're going to have 3 useful relations. First, we can write our beta vector. Now, we had defined it so far as a scalar beta equals v over c, but if we allow v to be a vector, we can define beta vector as v over c, the v vector over c, and this is p vector times c over the energy. So this is the spatial part of our 4 vector. So this tells you that if you know the velocity, you can get the momentum and the energy. That's nice and happy and comforting because we could do that classically. 2. And this one's really useful. A lot of problems in relativity involve manipulating algebraic expressions, and you have to find the right way to simplify the equations, and p squared equals negative m squared c squared all the time. This is really pretty awesome. And 3 E squared equals mc squared quantity squared plus p c quantity squared. And note here, I'm writing it as a vector because I want to make sure that I distinguish this. This is the 3 component of our 4 vector, whereas when I do not have the vector symbol, following the notation of the book, when I don't have the vector symbol, that means that I'm talking about the 4 momentum. So p vector quantity squared, c squared. So these two equations, really all 3 equations, are really useful when you're doing relativity problems because you are always looking for the right algebraic equation to simplify things, and you want to do it as simply as possible. So then you can take this, and you can then use this. Conceptually, it is sometimes useful to imagine this as a right triangle, where this is PC, and this is mc squared, and then this is your energy, which also happens to be gamma mc squared. All right, so then we can look at what this means, and we can look at the energy and momentum of an electron. So we'll start with there's different ways to describe this, and it's worth getting used to these funky units for mass. So the rest energy of an electron is about 0.5 eV. What that means is that that is equal to mc squared. So we often use the units of eV per c squared. I can just divide by the c, but I can leave it as a c. I don't actually have to put numbers in. So I can write my mass as 0.5 eV per c squared. And you will see this unit all over the place, especially when you are doing something in high energy physics. We use EV, MEV, this is an MeV, so our unit is 0.5 MeV, where an MeV is 10 to the 6th. So then you can calculate from this what the mass in kilograms is. So this is 0.5 times 10 to the 6th EV over c squared, where this is 3 times 10 to the 8th, or 9 times 10 to the 16th, squared, meters squared per second squared, times 1.602 times 10 to the negative 19 joules per, let me write that meter, joules per electron volt. And this works out to be the old familiar 9 times 10 to the negative 31 kilograms. Now, how can you double check that? So those of you who are watching this have always had calculators, and you know the cell phone in your pocket is way more powerful than the Apple II Plus that we had when I was a kid. So here, if you want to do what I like to do to double check my numbers, is calculate orders of, just track orders of magnitude, and it should be pretty dang close. So here, this is, I'm going to put my my numbers that are not powers together. So here I've got a 1/2, and then this is, the 3 is going to give me a 1/9, and then times 1.6. That's all of the numbers that are not powers of 10. And then my powers of 10 are 10 to the 6th minus 19. Here I get a minus 16. So here I have 6 minus 16, so I get a minus 10. So here I have 1.6 divided by 18 times 10 to the negative 29. And where I get those last, so here this is 16 over 18. That's going to give me something which is pretty dang close to 1/10. That gives me 1 extra power. And because it's just a little bit less than 1/10, that's where when you get the 9, you get an extra order of magnitude there. All right, so then we can consider what if this electron has a kinetic energy of 0.8 MeV. So let us say T equals 0.8 MeV. And I should have caught, when I forgot the M, I should have caught that because neutrinos are believed to have masses on the order of electron volts. But even the very tiny light electron has a mass on the order of MeV. All right, so let's assume we have a kinetic energy of 0.5 MeV. What is the momentum? And first of all, energy is T, the kinetic energy plus the mass energy. So this gives me a total energy of 1.3 MeV. And now we want the momentum. So here we have the energy and we have the mass energy. So we're going to use this form, energy squared equals P squared C squared plus MC squared quantity squared. And our momentum is E squared, the square root of E squared minus MC squared divided by C squared, all the square root of that. Okay, now a good physicist is a lazy physicist, so we're going to leave the C's. This is a unit of energy, that's a unit of energy, and I have 1.3 MeV quantity squared minus 0.5 MeV quantity squared, the square root of that, divided by C. And here you get 1.3 quantity squared is going to give me a number that is about 2-ish. And then minus a number which is 0.25. And then I take the square root. And all of this is going to give me, so I'm going to have a number that's a little bit more than 1. So this will never go above that, but it's a small correction. The mass is a small correction here. So we get 1.2 MeV on the top, and then we still have the C. And so we're going to write it as divided by C. So broadly, you can usually get away with these units with just leaving your C's as a C and not plugging the numbers in, but leave it as a variable C. And then if we want to get beta, we're going to use beta is PC over E. And now our PC, this number times C, is 1.2 MeV, and the total energy is 1.3 MeV, and so this works out to be 0.92. So we were able to get our beta and our momentum with relatively few calculations. It's all algebra. So then we can move on to collisions. And we're going to talk a lot about collisions because collisions are really important. They're really important because often when we talk about high energy experiments, for instance, how we find new particles, we're smashing one thing into the other, and how we understand how we measure what's going on with subatomic particles is largely by doing collisions and they're usually at energies such that relativity matters. But we're going to start by talking completely in the abstract, that you have a mass A, m sub A, that has energy E sub A. Think of it as colliding two lumps of putty, and you smash it against another lump, which has the same properties but with a subscript B. And we want to find the final mass of the lump. And now we can use momentum conservation, because relativistic momentum conservation has in fact been observed. So we can, first of all, we can write this. We know that the final momentum squared, since the two masses of putty stick together, so the final momentum squared, this was one of our relationships, p squared equals negative m squared c squared. Let me just put a note of caution that this form will slightly depend on how you defined the four momentum, and different books define the four momentum different ways. So always watch, just stick with a single book's notation. Don't flip between books without reading carefully. The final momentum, the final four momentum, has to equal the initial four momentum. So it has to equal PA plus PB. And we presume that mass A comes in with some, it is moving, and this guy is at rest. So then we can write PA as the 3 vector of the momentum times EA over C, and PB is zeros and MBC. So then we can take this expression, P fin squared equals negative m squared c squared equals PA squared plus PB squared plus 2 times the dot product of these two. Now, when I take the dot product, I have P vector times 0, so that's 0, and then I get an EA over C MB times C. So you can already see some convenient cancellations. Boom, boom. And this is negative m squared c squared equals negative ma squared c squared minus mb squared c squared plus 2EAMB. Except that, when I take the dot product here, I should have done the minus sign, because that was in our definition of the scalar product. All right, so then I have negatives everywhere, and I can solve this and get m squared equals ma squared plus mb squared plus 2EAMB over, for some reason that one's lowercase, over c squared. So if we are at non-relativistic speeds, then we get the initial energy is approximately MAC squared. And this becomes M squared equals MA squared plus MB squared plus 2MAMB, but this is just MA plus MB quantity squared. So you get that the final mass is equal to MA plus MB. So non-relativistically, we get what we expect. And in general, what we're going to see is that the final mass is going, so any difference from anything that is a non-relative, that is a relativistic correction is going to make this larger than MA plus C squared. So you're going to get a mass in general which is larger than MA plus MB. Now, notice we haven't really worked with the ugly messiness of vectors yet. We're actually going to be able to avoid, by being clever, some of the messiness. So our velocity is P. Our final velocity is P final C squared over E final. But this has to equal then the 3 component initially, PA C squared over EA plus MBC squared. And this is just from our useful relationship beta equals PC over E. And now now this is E, and my final momentum has to be the initial momentum. So I didn't have to do a ton of work. And then here, this also has to be gamma MAV, the initial momentum, the initial 3 momentum, over gamma MA plus MB. So here there really was, so there was the C squared, and here we've canceled the C squared on top and bottom out. So this is just energy is gamma MAC squared. So we can, and then we can see that our, again, non-relativistically, our final velocity, we're going to have gamma roughly equal to 1. Our final velocity is MA times, this was the velocity of A, I dropped the A there, over MA plus MB. And that is what we get classically. So we saw that we got classically, relativistically, we see that our expression relativistically reduces to our classical expressions for things that are moving at low speed, exactly like we need it to. We can then talk about the center of mass frame, or the center of momentum frame. This is the frame where the system is at rest. We often use this frame because it makes it easier to solve problems. So this is the frame where the total momentum, which is the sum of all of the momenta, is equal to 0. And in this case, the sum of all of the the vectors is time-like. So a benefit is that it is easy to solve collision problems in this frame. You often solve the collision problem in the rest frame of the particles, and then you transform it back to the lab frame. So we can look at this in an example where we have a head-on collision in the lab frame. So similar construction, but now, so we have A that is coming in, and B is at rest, and A comes in and smashes B. This is a common experimental setup because you often take a projectile nucleus and you smash it against a target nucleus. So then we can write PA is whatever the incoming 3 momentum is, EA plus MB, sorry, this is not PA, this is the total momentum. So we're going to use the same coordinates that we used before. So PA is P vector A, and then EA over C. PB is going to be zeros, and this is going to be EB over C, but EB is simply MBC squared, so we are left with MBC. And then the total momentum in the system is the sum of these two. So our total momentum is P vector A, and then we're going to write this as EA plus MBC squared all over C. And the beta of that system is just P, the total momentum, C over, the total 3 momentum, which is the same thing as just the initial momentum of A, over the energy. And now we can read off here that the energy of the system is EA plus MBC squared. So beta is PAC over EA plus MBC squared. And just so you guys get a little confidence, the reason I'm able to write this stuff down without thinking about it carefully is because I have notes. When you see me do it, it's a lot easier than I expect you to be able to do. What's different in relativity, in special relativity, oftentimes the math is a lot simpler than some of the other chapters that we've done. But you have to really think carefully to make sure that the equations that you're writing down are correct. All right, so now we know the beta for the rest frame. And then here, what I'm going to do is write lab and center of mass. So we are going to start in the lab frame. The initial 4 momentum of B is this. Now, I'm going to write down for convenience our Lorentz transformation. It is gamma 0, 0, negative gamma beta 0, 1, 0, 0, 0, 0, 1, 0, negative gamma beta 0, 0, gamma. And I'm writing it like that because it makes it a little easier to see how you, so what we're going to do is now apply the Lorentz transformation with this beta to the center of momentum frame. So I'm going to multiply my 4 vector by this matrix. And, ooh, I want to keep the same color. So I rotate by this matrix and I get, so I start out with a 0 in the 1 coordinate, but I get a component in the 1 coordinate, which is, so I have a negative gamma beta times my initial 4th component. So I have a negative gamma beta MBC now in my 1st component, and that's because here I have P1, P2, P3, P4. So when I multiply it, I get gamma P1 minus gamma beta P4. Gamma P1 is 0, so I have negative gamma beta P4. And then in my 4th component, I have negative gamma beta P1, and then I have gamma P4. Oh, and the in between ones aren't changed, so I still have 0, 0, and gamma beta, gamma and then P4, not gamma beta. Gamma and then P4, but P4 is MBC. So I can write this as gamma MB MB, said the right thing, wrote the wrong thing, times C times negative beta 0, 0, 1. And when I do the collision, the collision in the rest frame of the 2 masses, it looks like they come in, they bounce off, they go off with exactly the same momenta. So now I have my collision and my momentum, PB final, in the center of mass frame. I just flip the sign there. So I have negative MBC, positive beta, 0, 0, 1. All right, now I have to transform it back to the lab frame. When I transform it back to the lab frame, I use the same transformation, but now I flip the sign of beta. So now I get P final of B is gamma times P1. So I'm going to get a gamma in both places. So I get a gamma times P1, that's a beta, plus beta gamma times P4. So I get another beta there. And then I have zeros. Those zeros are not shifted by my coordinate transformation. And then I have gamma MBC, and then I have a gamma, oh, and that one I had the gamma squared. I have another gamma, and I get a here. Let me actually just write these to the side. So my P1 final, if I do this out carefully, is gamma MBC gamma P1 plus gamma beta P4. That's how I get the two betas and the gamma squared. P4 final is, yeah, I'm going to just keep my constants out in front. Now I have gamma beta times P1. So I get another beta there. And then plus gamma times P4. So here I pull the gamma, I have a gamma squared everywhere, and I have MBC, and then this last one I have beta squared plus 1. Okay, so that tells me my final momentum, and I have that my beta is PC over E. So this is my 3 vector. So if I want to only look at the magnitude, because I only have one component of the, I only have one spatial component of the velocity anyways. So my magnitude of my 3 vector is gamma squared MBC times 2 beta times another factor of C divided by my energy, which is, this one is E over C, so I'm going to multiply it by C. I have a beta squared plus 1 gamma squared MBC squared. Okay, so there's a lot of cancellations. And largely because I'm taking the ratio of things that share a bunch of common factors. So I get that my beta is 2 beta over 1 plus beta squared. And that was also the beta of the initial system. So I can plug this mess back in should I need to. And here, if we get, so it's interesting to look at the case where the masses are equal, because if the masses are equal, then here our beta, if the masses are equal, we're going to end up getting that the final velocity of B is equal to the initial velocity of A. So that's exactly what we would get classically. So we see a phenomenon which is threshold energy. So often when we talk about collisions, well, you imagine something coming in, something coming out. The two things smack together and come out. But really the same mathematical framework also works for decays or something which happens relativistically but not classically, which is that you end up with more particles after a collision than you had. Well, I guess you can have more particles classically if you're breaking something apart, but we can actually create mass now, so we're not constrained by that restriction. So we will collide things and we will see the production of new particles. And this is actually how basically most subatomic particles were discovered, some form of collision. Now, I say most because sometimes you're talking about observing things from radioactive decays or from cosmic rays from outer space, and that was actually how something was discovered. But when you have a collision, you have a much more controlled environment, so you can change what goes in and what goes in, so that you know what went in, you can tell easier what went out. So you have examples like a proton smacking a neutron and producing a proton and a pion. So we say that, so you produce the pion. And then you have a proton smacking a proton, leading to a proton and a proton and a proton and an antiproton. And these were actually the collisions which led to the discovery of the pion and the antiproton, where this antiproton has the same mass, at least as well as we have measured it, and opposite charge. So there is a threshold energy when you have a collision such as this, which is a minimum energy for the reaction to occur. So you have to have enough energy if you're making an additional particle to make the particle. And note that these collisions explicitly don't conserve mass. So here you start with twice the proton mass and you end up with 4 times the proton mass. And here roughly you have twice the proton mass and you end up with twice the proton mass plus this guy, although the neutron and the proton mass are not exactly the same. Broadly speaking, we can consider a reaction where you have usually 2 things coming out. Coming in, it's easier to collide 2 things than 3. So even if you're trying very hard, it's hard to get 3 things to collide. And you have some untold number. And we're avoiding C because we reserve that for the speed of light. So in a traditional experiment, you have one thing at rest and the other moving. It does not have to be that way, but if you do that, then, well, first of all, often it was that way because it's easier to smack something which is moving into smack a projectile which is moving into something which is a target which is stationary than to collide 2 beams. Although we'll talk later about why we would collide 2 beams. But if you take something at rest and you smash it into something which is, or you take something which is moving and smash it into something at rest, then in the lab frame to produce you might first assume, so you have to end up with an energy at least above that. That's not actually good enough. We'll be a little more specific, but so here you have to do, so then we can look at the center of mass frame. So I should say this is true, but it's not sufficient. So we'll look in the center of mass frame, and in the center of mass frame, everything at the end can be at rest, which means that this inequality is true. So the sum over all of the final masses times c squared has to be greater than or equal to, or it has to be less than or equal to the total energy. So in the center of mass frame, the momentum is, if everything ends up at rest, for the threshold energy, the momentum is the energy divided by c in the fourth component, and everything else is 0. In the lab frame, let me try to stick consistently to a capital A and B for my subscripts. It doesn't matter what I do, I just need to be consistent. We're going to use PA, our old friends. And then because the scalar product is invariant, P lab squared has to equal P center of mass squared. And so then we can write this out. E center of mass squared, negative E center of mass squared, C squared. So here I'm taking that guy, has to equal, this is going to give me PA squared plus PB squared, and then plus 2PA PB. And this first one is negative MA squared C squared. The second one is MB squared C squared. And then this is this dot that minus this dot that. So I end up with a negative 2 EAMB. And I can solve this for EA equals E. So I'm going to multiply through by a C squared so that I have units of energy everywhere. I have EA squared, no, EA not squared. Let me start with, my negatives cancel out throughout. 2EAMB is equal to E center of mass squared, and then minus MA squared C to the fourth minus MB squared C to the fourth. And then I'm going to divide through by my 2, oh, and this should have had a C squared. Yes, because I multiplied through by C squared. So I divide by MBC squared. And I can erase this here. So this is my EA. And then I can, so that tells me the minimum EA if I am at the threshold. And I am going to use that E center of mass is the sum, at the threshold, is the sum of the final masses C squared. So here, I plug that in here, and I get that the sum of the squares of the final, the square of the sum of the final masses minus MA squared minus MB squared divided by 2MB all times C squared is my threshold energy. I'm going to clean the board up. And we can talk a little bit about, before we do an example, about what this actually means. So this is saying that you need, in the lab frame, you need for your projectile to have a minimum energy in order to produce the mass products here. If you have less than that energy, you're only going to get out what you put in. You might not have an, or you will get a different reaction. So you're not going to, but once you get higher and higher in energy, you're going to start seeing new reactions take place. And this is why when we do collider experiments, we always want to increase the energy, because we want to increase the number of particles that we can create. And we got this simply by looking at momentum conservation. You need enough momentum to produce the particles that you're talking. We call it momentum conservation, but we have this handy dandy equation that actually wraps up momentum and energy conservation into one, because it is for momentum conservation. All right, so then we can look at an example, and we can look at this example of protons colliding and making a proton and an antiproton. So, in this case, the sum of our final masses is 4 times the mass of the proton. So we look at this equation. The minimum energy required is 4 times the mass of the proton squared, so we get 16 MP quantity squared, minus mass of the proton minus mass of the proton, 2 mass of the proton quantity squared, divided by 2 times the mass of the proton times c squared. So 14 minus 2, or 16 minus 2 is 14, divided by 2 is 7 times the mass of the proton, c squared. So, and then this is equal to the initial mass, the initial mass of the proton, c squared, plus the kinetic energy of the projectile. So then your kinetic energy minimum is approximately 6 times the mass of the proton quantity squared. And this works out to be about 5,600 MeV. And this is actually where, so when the antiproton was first observed at the bevatron, it was at 5,600 MeV. Another example, you can take the J psi. The book calls it the psi. I have always called it the J psi. You can have electrons colliding, so at least in principle, you can have an electron and a positron collide and make a J psi. I think the book calls it a psi because it means you only have one variable. Almost all the literature calls it a J psi. So then the mass of this J psi, we now know, is about 3,100 MeV per c squared. And then the electron mass is, so you ask the, so here you have roughly, so EA is roughly m psi squared, because we can kind of, well, actually, because they're totally obliterated, minus twice times the mass of the electron squared over twice the mass of the electron. And this guy is approximately 0 compared to that thing. So and then times c squared. So here you end up with, because the electron is about half an MeV, so you end up with 1 MeV and on the bottom, and here you end up with 3,100 squared, or about 10 to the 7th MeV on the top. So if you want to produce a J psi by taking taking a positron and smacking it into an electron, in practice what you do is that you take your positron beam and you smack it into some type of atom, and it hits an electron in the atom, but you move the electron fast enough that you can neglect the motion of the electron. You move the positron fast enough that you can neglect the motion of the electron in the lab frame. If you want to do it that way, it takes 10 to the 7th MeV. So for context, the Large Hadron Collider, which is the fastest collider, the highest energy collider that we have made to date, produces beams which each individual beam is on the order of 7. Now, these are not electron beams, but we'll ignore that complication for the moment. It produces beams which are on the order of 7 terabytes, which is 7 times 10 to the 12th EV, and this 10 to the 6th times 10, or 10 to the 7th times 10 to the 13th is 10 to the 13th electron volts. So here, the highest energy that we have ever produced a beam at is not quite high enough to produce a J psi with a collision if you were to take a positron and smack it into an atom. The way that you get around this is that you use colliders, because that gets the most energy in the center of momentum frame. Which is, of course, why a lot of the times when we have discovery experiments, we produce colliders, which involves, well, today we have colliders that involve steering two beams and making two beams of subatomic particles smash into each other, which is very hard, but we have managed to do it. Now, we have not yet talked about the definition of force in relativity. So this is not as important in relativity, because we are often, at least in what we've talked about, because we're often talking about collisions, and we're dealing with things like the production of particles. We're not so much considering what happens when we deal with, for instance, an arbitrary force on an object. Now, the real answer, I think, is a little bit more interesting and subtle than it was discussed in the book. It's not just that it's more complicated. It turns out that we can handle, to some extent, the electromagnetic force, and the weak force doesn't even really come into play because if we start talking about the weak force, we have to use quantum field theory, and we're in an entirely different domain. And if we talk about electromagnetism, we can kind of handle it. And then if we're talking about gravity, we have to move to general relativity. Most of the time when we are talking about relativity, even though when in a real scenario, even though we have these book problems imagining a spaceship traveling at relativistic speeds, for the most part, in the things that we've managed to do to date, we're not talking about macroscopic objects moving at relativistic speeds. We are talking about subatomic particles moving at relativistic speeds, or maybe at most atoms or molecules. When we talk about macroscopic objects, it's things like airplanes, and the force that we have to worry about there is not the electromagnetic force or the weak force. It's gravity, but gravity involves general relativity, which we are not covering. So forces overall are not as important, but they can be more complicated. We still have some toy problems that involve forces, and we want to consider what the force would look like, but more importantly, we want to work towards how we do what we can, which is addressing the electromagnetic force. So we can define force in several ways, but we want a useful definition. And we want something which reduces to our classical definition in the region where it should broadly agree. So if, for instance, if you use a variable mass, then, how does that make sense when you involve relativity? Because it would change with the frame. So we're going to confine our discussion to forces which do not change the mass. So if you had some of these, if you had some force which changes the mass, which can be the strong force or the weak force, that is a whole nother ballgame. But we can think, when we say confine ourselves to forces which don't change the mass, what we really mean is the book calls it the Lorentz force when you're talking about the electromagnetic force, or basically fictitious forces that we're making up so that we can do some simple problems. If we're not talking about subatomic particles, then we really aren't talking, you can't take a proton and push it against some surface or let it roll down an inclined plane, because then you have to worry about quantum mechanics and the fact that you're dealing with a particle and not a macroscopic object. But we can still write it down and do some toy problems on it so that we have something we can work with. So this is our Lorentz force. And it turns out that the most useful definition of a force is that it is the time derivative of momentum. So classically, this is one of the things that you came across. This is not the same as the relativistic. This will agree with the non-relativistic force for low speeds. And with this definition, the force on a charge Q is given by the Lorentz force, which is what we want. And it turns out that we can come up with an equivalent of the work-energy theorem. So when we had this before, you could say you could relate changes in an object's kinetic. When we talked classically, you can relate changes in an object's kinetic energy to its to the force which was applied. So we're going to start with one of our favorite equations. This guy right here. And we are going to take the derivative with respect to time. So here, e dE dt equals, here I'm going to actually just start by, I'll leave the 2's in, and we're talking about things that don't change the mass, so this is a constant. So here I have 2pc squared dp. Let's see. Yes, this was a p squared, and so this is dp dt. So I can write this, so obviously my 2's cancel out, and I can write this as dE dt equals pc squared over E dotted with, now this is, here when I took the derivative I should have left this as a dot product. But of course P dot P is not very interesting. All right, P dot dP dt now. So this is, so I have a p c squared over E dotted with the force. Except another one of, so I had beta equals PC over E, or PC squared over E is the velocity. So this is just the velocity dotted with the force. Well, that's actually pretty interesting because that looks very familiar. So my change in energy is equal to F dot dx. So this I'm now using. This is dx dt dot f. So I multiply through by a dt and I get dE equals F dot dx. This is exactly what we had classically. And I can choose, because E equals mc squared plus t, and we have kept the mass the same, so this is the same as dt, a change in the kinetic energy. So what we see is that a small change in the kinetic energy is F dot dx, our old familiar friend. So now we can go with one of those imaginary forces that I was talking about. The thing that can never exist, we will imagine that we have a force which is simply a constant acting on a particle, and we want to find, we start at rest at the origin so that when we do integrations we don't have all these extra constants, and we're going to find how that particle moves and describe its motion. So P is the integral of dP dt with respect to t, and this is just the integral of f dt. So given that we start at the origin, this is ft. So far so good. So we have a constant force that ends up at ft. And then we're going to get a useful expression. So we can start with beta equals pc over E, and E squared equals p squared c squared plus m squared c to the fourth. And then we're going to get an expression for gamma. Gamma squared is 1 over 1 plus beta squared, which is E squared. So here I am going to use this definition. So let me do a few more steps than in my notes. 1 over 1 plus p squared c squared over E squared, multiply it through by E, and then here I'm going to use this definition. So here I have p squared c squared plus m c squared squared. Now here I have, that's because, I was a little suspicious. All right. And I've been doing this for a few decades, so if I make that mistake, you can too. All right, now E squared minus P squared C squared gives me c squared quantity squared. And this leaves me with 1 plus p squared over mc quantity squared. And that is equal to gamma squared. Now, I have P equals Ft. So I have gamma equals, gamma squared is 1 squared F squared T squared over MC squared. P is also gamma mv. So V is P over m gamma. And then I'm going to use this expression. I'm going to use this expression for P and this expression for gamma. And so this tells me that the velocity is Ft over m1 plus Ft over mc quantity squared, and the square root of all of that. So we can then look at small t. So at small t, the particle starts at rest and we are slowly accelerating it. For small t, then this term does not actually matter much, and we end up with the velocity is Ft over m for small t. Now, when the force gets large enough, these speeds approach being relativistic, and you have a gamma which is larger than 1, and you have to include the corrections. All right, so then we can look at when, I want to do this, the book didn't go through it, but what happens when t goes to infinity. So we want to look at the limit, and please be a little forgiving. I was lazy and didn't write the notes out in gory detail. So here we want to look at the limit when t goes to infinity of Ft over m times the square root of 1 plus Ft over mc squared. Now in this case, if you take the this, you have infinity over infinity, so you have to take the derivative of the top and the bottom, or you can take the derivative of the top and the bottom. And when you do that, you get F over m times 1/2, 1 plus this mess to the negative 1/2, which means it's going to come up to the top, times 2Ft over mc. All right, and then this simplifies to here I have these factors of 2 which cancel out, that cancels out, and I have an F on top and bottom. So I have a, here this is a divided by C, so I have C times 1 plus Ft over mc quantity squared, and then it's to the half, and then divided by t. So here I then would take the derivative again, because again I have infinity over infinity. And I have just a little circular. This should have been to the negative 1/2. And then divided by 1. Eventually you will see that this in fact equals c. So as t goes to infinity, the object approaches the speed of light. And then the position is going to be the integral of the velocity and when you take, so this is an integral, so when you take this integral, you're going to get force over m, and then here you would do a u substitution for u equals ft over mc. Actually, this should be a vector. Ft over mc. And you will get, I'm going to leave this as, I will leave the integral as an exercise for the student. Or you can do it either by u substitution or by looking it up in an integral table. And to get you would have an integration constant. If we want the position to start at 0, because at t equals 0, this is 0, you need to subtract off a 1 to get it to the origin at t equals 0. We can then ask about the potential energy, because if we have a kinetic energy, we have a potential energy. And we will have at least one frame. So we are going to look at forces where there's at least one frame where the force is conservative, meaning that there is some potential, which is so that you can write the force as the gradient of the potential. An example is a charge moving through an electric field. And when this happens, f dot dx is equal to negative gradient of u dot dx, or du, negative du. And this is equal to dt. So you can rearrange this so that dt plus u is equal to 0. So if the force is conservative, what that means is that a potential exists, and then this is t plus u is conservative. We are then going to move on to the force. So we have defined the force, but so far it is only the spatial components of the force. So what do we want to be our force? So it is important to note that F equals dp dt cannot be the spatial part of a 4 vector, because of the same problem that we had earlier. You're taking a 3 vector and dividing it by something which is not a scale, you're taking something which is part of the spatial part of a 4 vector and dividing it by something which is not a 4 scalar. So this cannot be the spatial part of a 4 vector. So we will go with so it's similar to the problem with velocity transformation, because we will not conserve the form of the force when we change coordinate systems. So we will instead define the 4 force to be dp, the 4 momentum, dt naught. And note that there are several notations for the 4 momentum. We are sticking with the books. And for the 4 force. So we're sticking with the books, K. Since this is a 4 vector and this is a 4 scalar, this is automatically a 4 vector itself. So K is going to be K, the spatial part, and this is going to be, because it's the time derivative of the momentum, that with respect to the proper time, this is then dp gamma times dpt, d time, not the proper time. And then here you have 1 over c dE dt. And we can also write gamma equals this, and then the velocity dotted with the force over c. So this transforms through a Lorentz transformation because it is, in fact, a 4 vector. This is an advantage. A disadvantage is that we have the derivative with respect to the proper time and not to the time, which means that it might not always be as useful. Relativistically, there's a phenomenon that occurs that doesn't happen classically, which is massless particles. So, classically, when we talk about momentum, we have momentum equals mv, and kinetic energy then is 1/2 mv squared. So if you have these expressions, you cannot have a massless particle. It has no momentum, it has no kinetic energy. Well, you could have one, but it would have no momentum and no kinetic energy. So what would it be? But relativistically, we have a few different expressions. So we have now derived for the 3 momentum this form, and for the energy gamma mc, now squared. Now these also look like you would have no momentum and you would have no kinetic energy if you had no mass, but we have different expressions. V over c equals pc over the energy. This does not depend on the mass. And energy squared equals mc squared, quantity squared, plus pc, quantity squared. So here it depends on the mass, but it's not 0 if the mass is 0. So if we take these expressions and we set the mass equal to 0, then you get that the energy is p C. And you would get the same, so here there's no dependence on energy. You set V equals, so the consequence if P is equal to C is that V over C is equal to 1, and that then the speed of this particle is the speed of light. So in this case, relativistically, you in fact can have massless particles, and they have they travel at the speed of light. You could see here that you cannot tell if you would have massless particles because if you had a massless particle, you would have 0 divided by infinity. And you can't tell what that is. You would have to take a limit, and it's unclear what that limit is. So even these expressions relativistically are ambiguous, and you have to go to these expressions to see what would happen. So massless particles do in fact exist, and they always travel with the speed of light. And they also have, so their 4 momentum, like any 4 momentum, is equal to 0. And we can actually see that now that we know what the energy and the momentum, how to relate the energy and the momentum, because the 4 momentum is P and then E over C. So P squared has to equal negative MC squared, and that is equal to P squared minus E squared over C squared. But now P is E equal to E over C, so this is just E squared over C squared minus E squared over C squared, which is equal to 0. So then we can look at massless particles will travel on the forward light. If they're traveling forward, they'll travel forward on the forward light cone. So they're forward light-like. And then we can talk about what happens with them. Now, we still have our conservation laws. We have conservation of energy, conservation of momentum. So, for instance, if you have something where you say have an excited nucleus and it emits a photon and de-excites, then you still have momentum conservation. So we are then assuming, of course, that our energy is the momentum times c, or that the momentum is the energy divided by c. And if you use this, you in fact find that energy and momentum are still conserved. We also can take a result from quantum mechanics. The energy of a single photon is h bar omega, where h bar is 1.05 times 10 to the negative 34, which is also equal to h over 2 pi. And then the momentum, P, is going to be h bar times the wave number. So the 4 momentum is then h bar k, where k, the 4 vector k, is the 3 vector k, giving the direction of the wave, and omega over c. So if you multiply, so then that would give you P equals h bar k, and then h bar omega over c, but this should just be P vector E over c. So here, then, because the energy is a 4 scalar, and this is here, this is going to be related. So this is just a scalar times a 4 vector. This is in fact itself a 4 vector. So this is relativistically invariant because both sides are 4 vectors. We can then look at the magnitude of this. It is h bar, let me bring this down just a little bit so that you can read it. The magnitude of the 3 vector, the spatial component of the momentum is h bar times k, which is 2 pi h bar over lambda or h over lambda. And this is the de Broglie equation, the de Broglie relation. Now, specifically for photons, our 4 momentum is then you can write this as h bar omega over c, a unit vector in the direction of the propagation, and 1. Now, as soon as we have a particle, we can do our favorite things with it, which means that we can smash it into something. That is what we love to do. We love to smash things into something. So, if you have a particle that carries the photon, and it is what carries the energy in light, it can collide off of other things. And the first thing that was proposed is Compton scattering. So you have a photon come in. We usually use the symbol gamma for a photon. It hits an electron. Now, technically speaking, this is usually an electron in an atom, which is not quite at rest, but it has roughly 0 momentum, especially compared to, it has roughly no velocity, especially compared to the light. Now, then the photon will recoil, and it will, so it leaves here. It has a momentum p gamma at the end. Here it has a momentum p gamma 0, and it makes an angle theta here, and the electron will go off with some momentum itself. Classically, what would happen is that the photon can absorb, the electron can absorb energy potentially from the photon, but that would change the photon. Well, it wouldn't have a photon. You wouldn't have a photon. The electron can absorb light energy, but it would not deflect it because the light can carry no momentum. If you had a particle come in and it's not carrying momentum, it would not really be deflected. But as soon as you have a photon as a particle, it can come in and scatter off. And what happens is that now the photon has given some of its energy to the electron, so the photon has a slightly longer wavelength or lower energy. And we can then write, so we're going to derive the equation that describes what happens to those wavelengths and the wavelength as a function of the angle of deflection. So we will use momentum conservation. We have that we will write the 4 momentum of the initial particle, the initial photon. It's this. The 4 momentum of the final particle will be the same, except that we will not call omega omega naught. We will just call it omega. We will not call our k naught. We will just call it k. And the initial momentum of the electron is zeros and mc. So, by conservation of momentum, the initial momentum is equal to the final momentum. So we have p naught plus p gamma naught equals p gamma plus p. We will rearrange this. P naught plus p gamma naught minus p gamma equals p. And then we're going to square it. So we get p naught squared plus 2 p naught times the difference in momenta of the photons plus this thing squared, which gives us a p gamma naught squared plus p gamma squared minus 2 p gamma naught p gamma, and that all equals p squared. So we can do some straightforward substitutions here. This is because anytime that we have a particle, so we have our result that the four momentum squared is negative mc squared. So we can use that. So here we are left with negative mc squared, where this is the mass of the electron. This term doesn't simplify yet. These two terms are 0 because the mass of the photon is 0. We have this term doesn't simplify, at least not. We won't do anything with it yet. And here, this one is negative mc squared. So then here we can take note of the fact that there's a negative mc squared on each side. Conveniently enough, we will move this guy over here, and we are left with 2 p naught p gamma naught minus p gamma equals 2 p gamma naught p gamma. And now we have all of these terms. So this is going, oh, and this should be a dot product in there. I should write the dots because there are slightly different meanings. If you say, later we will talk about tensors, and it has a slightly different meaning if you are doing tensor multiplication or a dot product or matrix multiplication. All right, so then here we have these terms. Oh, we're going to go ahead and cancel out the 2's because we don't need to carry that along. So here we have 0 mc dotted with h bar over c omega naught minus k, or sorry, omega naught k hat naught minus omega k hat and then that's the spatial direction, and then here we have omega naught minus omega, and this has to be equal to this dotted with that, so that is h bar squared omega naught omega over c squared. And then here we have k naught hat dot k hat minus 1. All right, we can make some more convenient cancellations here because we have h bars and c's that we can cancel out. This term doesn't come in at all because we have that, and we are left with mc omega naught minus omega equals omega naught omega over c and then here, this term, k hat naught dot k is just going to give us cosine theta. So we have cosine theta minus 1. So we can move, I'm going to divide through by omega naught omega MC and these guys cancel out. I dropped an H bar here. I didn't carry over my H bar. And I am going to multiply through by a -1. So I get omega minus omega naught over omega naught omega, which is let's see, I think here I should have yes, when I did this dot product, this term should have had a negative. So I should have switched that, and then this becomes that, and I am left with 1 over omega minus 1 over omega naught equals h bar over mc squared times 1 minus cosine theta. Omega equals 2 pi over c, or sorry, 2 pi over lambda. Two pi c over lambda. So here, this is from v equals lambda f, which is 2 pi over 2 pi omega, no, omega over 2 pi. F is omega over 2 pi. And then this is lambda. So I can, and this has to equal c. So omega equals 2 pi c over lambda. So here, 1 over omega is lambda over 2 pi c. So I get lambda, I'm going to multiply through by the 2 pi c. I get lambda minus lambda naught equals 2 pi c over mc squared times h bar 1 minus cosine theta. 2 pi times h bar is h, and one of those cancels, so you get h, lambda minus lambda naught, equals h over mc 1 minus cosine theta. So if you have Compton scattering, you have a photon scattering off of an electron, you get a shift in the wavelength. Now, what is the important stuff? I don't expect you to remember, so here we kind of knew what we were looking for. We wanted to derive the classical Compton scattering, but you know, there's a whole bunch of different ways to do it. If you weren't trying to get at this form, you equally well could have stopped. I mean, I might have stopped somewhere here. Omega naught minus omega equals this. It's a little, well, is it uglier? It's about the same, but we have typically measured things in terms of wavelength shifts. So then what you will see is that the amount of wavelength shift that you see from the scattering depends on the angle that the outgoing photon makes with the incoming direction. Now, many of you guys have heard the term tensor, and I know from talking to my students that you guys are a little intimidated by the term, and you feel like it's something scary. It's not. Let's start with a vector. Well, a vector is a specific type of tensor. It is a tensor of rank 1. Now, I can put a few different numbers. I can put them in the form of a vector, but that doesn't make them a vector. So I could have the energy of the system, the temperature, and the volume. These are 3 numbers that may describe a system, but they are not a vector because they do not rotate like a vector. They do not transform like a vector. So vectors themselves, although we don't, you think of them as a collection of 3 numbers, but it's more specific than that. They're 3 numbers that have to transform, for instance, under a specific way, under rotations. So if we start with how does a vector transform, and we'll stick with a 3 vector for this, at least so far for this discussion. A 3 vector can be rotated by a rotation matrix R, so that if A is a vector and I pass it through a rotation matrix, I get A prime. So here, this is notation with vector symbols. I like to have capital R's, capital letters for my matrices or tensors. I prime, we can also write, so this is the ith component of A, is the sum of Rij, Aj from J equals 1 to 3 in the case of a 3-dimensional vector. So this is index notation. And we use indices for each of the different components. And later, if you take more advanced classes, you will often sometimes just use notation like this, where repeated subscripts implies a sum over those 2 subscripts. This textbook does not use this notation. You will come across it in other textbooks. Now, the scalar product is invariant under rotations, and what that means is if A and B are both vectors, A dot B is the same thing as A prime dot B prime. So if I rotate A into some other coordinate system, and I rotate B into some other coordinate system, so it doesn't, the dot product doesn't matter, does not depend on the coordinate system that I use. And that should be because we have a physical interpretation of the dot product. The dot product is the product of the two magnitudes of the vectors times the cosine of the angle between them. So if it's that definition does not depend on which coordinates system you use. Now, the book distinguishes, so it calls this vector notation and calls this matrix notation. A vector transpose, a dot product is A vector transpose times B vector. What that means is here, if you do a dot product, you have to do A1, A2, A3. You have to have a row matrix times a column matrix. B1, B2, B3. And if you do matrix multiplication, this is A1, B1 plus A2, B2 plus A3, B3. So these are all sorts of different notations to say the same thing. It is worth it to get to know these different notations because they come up over and over and over again in physics in different books. So normally if I'm going to throw something at you, I'm going to do it because I think that it is useful. I don't believe that you should be learning what one of my colleagues calls esoterica. All right, so then here we're going to use, because these two vectors transform under rotations, we get A prime by taking R times A. So we have R dot A times R dot B. R times A times dotted with R times B. And this, if you have, I will leave it as an exercise for the reader to show that here, this is the transpose of A. So I've taken the rows and made them columns. So I want to take the transpose of RA and multiply it by R. Oh, I've just switched my ways of writing capital R's in one board nonetheless. It's really entirely arbitrary, but I should stick with the same notation in one board. All right, so this is RA transpose RB, and we will leave it as an exercise for the reader to show that the RA transpose is A transpose R transpose. So this is my full mess. Now, if this is to equal that, A transpose B equals A transpose R transpose RB, then multiplying by R transpose R has to be the same thing as multiplying by the matrix equivalent of 1, which is the identity matrix. So that tells me that R transpose R has to be the identity matrix. And this turns out to be true for any rotations. I will leave it as an exercise for the student to show that it is true. What that really means is it's a bunch of dumb, ugly algebra, but it's not actually anything. Actually, I could do one quick example. It's not anything super elucidating. If we do 2 dimensions, in 2 dimensions, R for a rotation about an angle is cosine theta, negative sine theta, sine theta. So if I take this and multiply it by so R transpose is cosine theta, and here I flip this column becomes the first row. So here I have a sine theta, and then this column becomes the second row. That's what it means to take the transpose. So I have this times this. And here I get cosine squared theta plus sine squared theta, negative sine theta cosine theta plus cosine theta sine theta, and then negative cosine theta sine theta plus sine theta cosine theta, and then here I have sine squared theta plus cosine squared theta. So this is indeed equal to the identity matrix. And you could take some of the forms, the different versions of writing it with in 3 dimensions, and you could multiply the rotation matrix by its transpose, and you will see that it is 1. You can also think about this as the, so here, this is a rotation through an angle theta, but if you flip it, it's a rotation through an angle of negative theta. So if you rotate your coordinate system first by positive theta and then by negative theta, you end up back where you were. And by the way, this property also means that you have an orthogonal matrix. And we also say, in this case, it is unitary because it ends up being the identity matrix. All right, so just like a vector is a collection, if we stick to 3 dimensions, of 3 very special sets of numbers. It's not just any 3 numbers they have to transform under a rotation. A tensor of rank 2 has 9 elements. So T11, T22, T33, T12, T13, T21, T23, T31, T32, T. So a tensor you write like that. And so if it is a rank 2 tensor, it is 2-dimensional. And what we cover here only covers through rank 2, but you could have a rank 3 tensor or higher. You just increase the number of indices. I just cannot write it on the board like this. In general, a rank n tensor, a 3-dimensional rank n tensor, will have 3 to the n coordinates. Now, of course, we're going to move into 4-dimensional tensors, which, so a rank 3 4-dimensional tensor would have 16 coordinates, which is 4 to the 2. And if we take a tensor, Tij, and it has elements so the element Tij is Ai, Bj, where A and B are vectors. Now, before, when we wanted a dot product, we took a row matrix and multiplied it by a column matrix. We actually now can take a column matrix, A1, A2, A3, and multiply it by a row matrix, B1, B2, B3, and then we will get A1, B1. So here, A1, B1, A2, B1, A3, B1, here I have I'm always going to have an A here. So this if I want to write it in matrix notation, A vector times B, or A. So when I wanted to multiply a row vector by, I had a 3 by 1 matrix that I was multiplying by a 1 by 3 matrix, and I got a 1 by 1 matrix. I think actually, do we say what? No, we switched the order of the indices. A 1 by 3 by a 3 by 1, 1 row, 3 columns, multiplied with 3 rows, 1 column gives 1. Here, a 3 row, 1 column matrix multiplied by a 1 row, 3 column matrix gives a 3 by 3 matrix. Now we want to look at the transformation properties of this tensor we've just created. So, T prime ij equals ai prime bj prime. And this is rik a cot k and the sum over k times the sum over L rjl bl. So here I have just rotated each of the individual components, and this is equal to the sum over k and the sum over L, where each of them run from 1 to 3, r I k r j l, and then this is t k l, because ak times bl is tkl. And I can also write this as my rotation matrix times my tensor T times my rotation, the transpose of my rotation matrix. So what you see is that the way that this tensor transforms is it also transforms with the rotation matrix. So any three-dimensional second rank tensor is going to transform like this, and anything which transforms like this is a three-dimensional second rank tensor. Now we want to see what a tensor times a vector is. And you've actually already seen this if you remember last semester. Sometimes that's a big if. The angular momentum is the moment of inertia tensor times A, and times the angular velocity. Now, at that point in time, you might have wondered why I called this guy a tensor. It acts like a matrix, and in many ways you could treat it like a matrix. A matrix is a tensor is a special case of a matrix. In this case, the components of the matrix very much have to do with your definition of coordinate systems. And it turns out that if you know how to rotate coordinate systems with your rotation matrix R, if you know your moment of inertia matrix in one coordinate system, you could simply multiply by your rotation matrix to rotate to the new coordinate system. So now we want to look at, if we take in general a vector times a tensor, is that a tensor? So we are going to look at B, and let us assume that B times some tensor T, or B is some tensor T times A. Now, B prime should then be T prime A prime. And I can replace T prime by R T R transpose. And I can replace A prime by R A. And then I can just choose to draw my parentheses in different places because there's nothing particularly, as you know, the order tells me how I have to do it, and it doesn't matter which one I do first. So I can take this, and this guy is just 1, our identity matrix. So this is R T B. It's RTA, but TA is just B. So this is R B, which is just B prime. So B, if I have a tensor times a vector, this also transforms like a vector. Conversely, if A and B are both vectors and B equals some tensor times A, then this has to be a tensor. This was, of course, all a setup to get us talking about what happens in 4 dimensions because this is relativity, we don't actually care about 3 dimensions that much as long as we're only doing it because it preps us for the thing that we're after. So now we're going to take a 4 vector, A dot B, and of course A dot B is A1 B1 plus A2 B2 plus A3 B3 minus A4 B4. So we will say that this is A transpose times G B, where G is 1, 1, 1, negative 1. And I just want to add a side note here that this is another one of those cases where this will vary depending on the textbook and the conventions that it has chosen to use. This is called the metric matrix. And the scalar product is invariant, and what that means is, so because A prime dot B prime has to equal A dot B, this means that lambda A transpose times lambda B, the dot product of that. So when we do the dot product, we're going to slip in our G lambda B. Then this means I have A transpose lambda transpose G lambda B. And because this has to equal A transpose B, this guy all has to equal the identity matrix. So if you remember, probably about an hour ago in this lecture, it was or 2, I started doing stuff where I was like, oh, well, Lorentz transformation, transpose times Lorentz transformation has to equal the identity matrix. It's because what stuck in my head was a different book's notation where this metric was all the identity matrix, which I kind of like better, but that's not the convention this book does. So this is then the analog of the rotation matrix transpose times the rotation matrix has to equal the identity matrix, except this is the analog for a 4 vector. All matrices which solve this, the set of all matrices which solve this is all Lorentz transformations is called the Lorentz group. Group theory is a wonderful thing, but it is not typically covered in an undergraduate curriculum. Okay, so then we can look at some tensor times A, dotted with A, and this is going to be the tensor times G times A. If this is any tensor, and so this is just saying how we denote the scalar product and how we have, so if we have a dot, it doesn't mean simple matrix multiplication. It means we got to slip that G in there. Now, I'm going to make some assertions that I'm not going to prove. By the way, what we're doing all of this for is so that we can talk about electricity and magnetism relativistically, and this book only touches on it a little bit. It's really, really meaningful. But we got to build up some math first. So we can also say that if T is any tensor and A is any vector, any 4 vector, then B is the tensor times the vector, has to also be a 4 vector. You can also prove that if this is a 4 vector and that's a 4 vector, this must be a tensor. And with that, we have some additional mathematical tools, and we can talk about electricity and magnetism in relativity. So we're only going to really focus on on electricity and in electrodynamics and relativity. What we're really going to focus on is the Lorentz force, which is the force experienced by a charge. And classically, we express this like this. We want to write this in a way that works for relativity. We had previously introduced the 4 vector for the force, K. My God, that's an ugly K. I can do better than that. K is gamma times the force, where this is dp dt, and this is dp dt naught. And we will use as well the 4 velocity, which is gamma v, gamma c. So we want to try to find a tensor for the Lorentz force where it has a form that looks kind of like this. So we want to look for a K, which is Q times some tensor F dotted with U. Can we find it? So we can take this and write out the components that we want. So we're going to look for, this would really, because this is a dot product, this is going to be Q, let me write it as a regular F. The book has a script F, and I cannot draw a script F. Capital is confusing enough. So we want to look for something that looks like this. Now, we can look at this equation and this equation and see that what we want, you can pick them out one by one. It's a pain in the butt. And as with many of the things that are done in Taylor, it is left as an exercise for the reader. And even though I am going through and explaining all of this in a lecture, I don't want to write it down. It's a lot. So your first component here, because you really have the 4 vector, and you have to, the first component of this force that we're trying to solve here has got to end up looking like this, because that's gamma F. That's gamma F1. And then you can swap out U and U, so gamma V2 is just U2, and gamma C is the energy over C. Oh, I forgot. There I have the energy. So here, this is the same thing as B, or QB3 U2 minus B2 U3 plus E1 over C U4, because U4 is gamma C. And if you do this meticulously and say, well, that has to equal these guys, and my 4th component has to be V dot F, or U dot, this U, 3 component V, or the 3 component of U. You can write out what the matrix should be, and you get FG equals 0, negative B3, B2, E1 over C, E2 over C, E3 over C, 0, negative B1, 0. I have zeros down the diagonal, and there's no particular reason why I'm filling them in this way. Other than that I have to pick something. Okay, so that's my mess. And then here, if I want, so because G squared equals 1, I can, if I want F, I can take FGG equals this matrix that I just wrote down times G, and I get, I'm going to actually not rewrite it, I'm going to delete my G and then change some signs. It's all these guys that change. So that tells me my force. And now for this particular F, my 4 force is Q times that F times F dotted with U. So this is now a 4 vector. This is a 4 tensor, which transforms under a 4 under a Lorentz transformation. So if I want to change my force, if I want to change coordinate systems, I can find this F by multiplying by a Lorentz transformation, my Lorentz transformation matrix. And just a note that this is anti-symmetric because F transpose equals negative F. So if I flip the rows and columns, it's equal to the negative of the original vector. All right, and the fact that this transforms under a Lorentz transformation means that if I want F in a different coordinate system, F prime is lambda F lambda T, because that is how a Lorentz transformation, how a tensor should transform under a Lorentz transformation. So, some of Taylor's favorite words. It is a straightforward but tedious exercise to show that with a standard boost along the x-axis, E1 prime equals E1, E2 prime equals gamma, E2 minus beta C, let me double check, yes, beta C B3, E3 prime equals gamma E3 plus beta C B2, B1 prime equals B1, B2 prime equals gamma B2 plus beta E3 over C, B3 prime equals gamma B3 minus beta E2 over C. Taylor does not shy from straightforward but tedious exercises, but when he specifically calls something out as tedious, it's a doozy. Okay, so the important thing to note here is that the electric and the magnetic fields get mixed up in the transformation. So you can start in one frame and have pure electric field. So let's say your magnetic fields are totally zero, and the electric fields kind of transform in a way you might expect. The magnitude changes, but it's still an electric field. But if you have, so you're moving along the one axis, and so there's no electric field then along the one axis, but in a different frame, you all of a sudden get a magnetic field from your electric field. So just changing the coordinate system gives you a magnetic field where you had none. And that is somewhat surprising. This means that the electric field, the existence of an electric field, requires the existence of a magnetic field in some coordinate system, and the converse. So that does provide us with a way to work this out, because remember, a good physicist is a lazy physicist. So if you can find an easier frame to work in, and you guys, depending on where you are, you may not have yet had an upper division an upper division electromagnetism class. Some of these problems are really hard to work out. If you can find a frame where it's easier to figure out what the fields are, you can work in that frame and transform it back. So if you have a moving wire, then you can move along with the wire and figure out the fields there and transform it to a frame where the wire is moving, because in the wire's frame it's not moving. And then you don't have to, you get, if you find the electric fields when you're moving with the wire, you don't have to find the magnetic fields as well. They come along for free. You just have to work with relativity and Lorentz transformations and 4 vectors. So, okay, maybe it's not the easier way, depending on how comfortable this is new to you, but we're building up your toolkit so you have more to work with. So, in fact, we are going to do that example. This is the one example that Taylor provides, and I actually find it kind of counterintuitive because then he moves it along the z-axis. Well, sheesh, why couldn't you just move it along the x-axis and make it a little bit easier for us? But no. So we're going to have a wire that has some charge on it. So it's a line charge, and it is moving with a certain velocity. Now we can solve this. We know what the answer is using our approaches from electricity and magnetism. We can do Gauss's law, Ampere's law, and figure out that if you have a line charge which is moving, the electric field is 2 times the Coulomb constant times the charge density per unit length divided by the distance from the axis in the rho hat direction. And the magnetic field is mu naught I over 2 pi rho in the phi hat direction. So we know this answer, but we're going to see that we can actually, oh, you can't read all of that. We're going to see that you can actually get that answer by moving with the wire and transforming your fields back. So E equals 2k lambda over rho hat. Okay, so what this gives you is that if you have the wire, if you look, so your electric field is radially out from the wire, and it falls off like 1 over r. And your magnetic field, if you're looking down the wire, wraps around. It's always pointing in this direction, so it runs perpendicular to r hat. So we are going to move with the wire, and of course with the wire we only have the electric field, so we can say that E prime is 2k lambda prime over rho prime, or written in vector notation, 2k lambda prime over, this one's kind of worn out, rho prime, and then we're going to multiply by the unit vector, which is x prime, y prime over rho prime. Now, it's important to note that rho is not equal to rho prime. So the amount of charge contained in a distance delta z is going to be lambda delta z, but in the prime frame, so this is lambda prime delta z prime, but delta z prime is gamma lambda prime, is gamma delta z. So we get that lambda prime equals lambda over gamma. And here I am going to do exactly what the book did, which is to tell you how to do it, but not actually write it out. So this is sketching how you would do it. You can take this result from the last section, and we want to switch it so that the boost is along Z instead of X. So how we're going to do that is that we're going to take all of the 3's and make them 1's, and make all of the 1's 3's. So every time I have a 3, I'm going to replace it with a 1. And every time I have a 1, I'm going to replace it with a 3. Boom. I have swapped the coordinates. I've swapped X and Y. And, yep, just making sure I did that all. All right, so then you find the inverse transform. And you can change it. Well, so here, this gives us, well, we would have to take, so the inverse transform, what we did here was swapping from the moving frame to the non-moving frame. So when we see a prime, we're going to make it a non-prime. And when we see a non-prime, we're going to make it a prime. And then we're going to come back, we're going to flip the sign of beta. Because if you are at rest and the thing is moving this way, so your velocity is in the positive z hat direction. Now, if we're moving with the wire, we see the rest frame moving at the negative z hat direction. So we're gonna flip the signs for beta everywhere, which is really just 4 signs. So now I have found the inverse transformation. And then I can take my, so here this is E1, this is E2, and I have no E3 and I have no B's at all. So I still have, and this actually, the book wrote the answer down, and let me just double check that I got the exact, yes, the book did not change the sign of beta, but you will also need to change the sign of beta. And when you do this, and I am going to leave the dumb math, I'm sorry, as an exercise for the student, you will see that you get the electric field So actually the reason why, so here, when the book does that transformation, it doesn't impact the electric field at all because you are starting with 0 magnetic field. So you get, for your electric field, E3 stays the same, and you get E2 prime is shifted by gamma, and E1 prime is shifted by gamma. So your electric field is just, and this should have had a prime, your electric field is just gamma to K lambda prime over, now it's a rho squared x, y, because you have shifted the, and then 0 because you've shifted the coordinates. And then because lambda prime is lambda over gamma, this is just 2k lambda over rho, rho prime. Now, when you, I think the book actually, yeah, I think the book actually has a sign error. Then for your magnetic field, you have a beta over C, and then gamma. So you have beta gamma over C, and then the magnitude of E and then for your one component, this is where I get a sign difference. I have a, so here this is a E2, so you have a, I have a positive Y, negative X, 0, and I disagree on the sign with the book. And this here, these constants, here, gamma, beta over C, and then we have, I'm okay with the rho, the Coulomb constant, and the factor of 2. I'm left with, we'll just keep lambda prime, and then the rho, because rho, there shouldn't be a, this over rho is a, small note. Here, we could swap rho prime and rho because the length along the, when we're moving in the z direction, the length along the x and the y direction doesn't change. So it's a small sleight of hand the way the book did it. You can swap rho and rho prime because they happen to be equal. If you were dealing with motion in the z, if you had a z component, you could not get away with that mess. Okay, so I have, these are my constants, and I am going to substitute out. So I have a gamma. For my beta, I'm going to put V over C. So I got a V over C squared. For my K, K is 1 over, let's see, I want to use K, K equals 1 over 4 pi epsilon naught, which is also equal to, let's use the books, K over C squared equals mu naught over 4 pi, so K equals mu naught C squared over 4 pi. So here I'm going to replace the K by mu naught C squared over 4 pi. My lambda prime, I'm going to call lambda over gamma, and I'm going to bring along my rho. And now, so here, going through that again, 2 gamma, beta I've replaced by V over C, K I replaced by mu naught C squared over 4 pi, lambda prime I have replaced by lambda over rho, and the rho just came along for the ride. My C squareds cancel out. 2 of those 2's cancel out. One of those 2's cancels out. My gammas cancel out, and I am left with V mu naught lambda over 2 pi rho. And that is what we are expecting. So this is then phi naught. So, and that's a relief because I didn't write as many details in my notes as I just went over with you. I did it winging it and it worked. So we started with Gauss's law. We started with just the field from a line charge, and we moved a lot. We said, well, we're moving along with the line charge, so it is at rest. And now we're going to take the electric field in the frame of the moving line charge and transform it back, and we see that we get the correct magnetic fields, which normally we would have with our standard electricity and magnetism skills, we would have had to derive using Ampere's law, but we got it for free. So that is really cool. There's a lot of other approaches you could take, transforming forces and moving back and forth between different frames. A lot of that is more advanced than undergraduate classical mechanics, but now at least you see that electric fields, when you change coordinate systems, electric fields change into magnetic fields and vice versa.